So, good morning, Kavanada. Good morning. Please kindly confirm audio, video, and screen once. Please kindly confirm audio, video, and screen. Okay, fine. Let's start with the next chapter. What we said the previous class, that is underground cables. Underground cables, right? See, first of all, what is the basic difference you can find between underground cables and overhead line insulators? Okay, 1 minute, please. So what is the basic difference we can find between the underground cables and the overhead line insulators? That's the first thing we are going to discuss here. See, in case of underground cables, generally we used to keep the insulation on the surface of the conductor. Insulation on the surface of conductor throughout the length. Whereas in case of overhead line, we will be keeping that insulation between the tower and the power conductor. Between tower and power conductor, we are going to keep the insulation. Okay, yeah, that's the difference. So I can say underground cables. Insulation kept on surface of conductor, or you can say core, anything. Conductor or core throughout the length. Throughout the length, we are going to keep that insulation on the surface of the conductor. Okay. That's one thing. Next. Some other differences, let me take up quickly. Some other differences between the cables and overhead line system. Look here, please. Look here. So I'm saying on this side, overhead line, just physical view of that, just you think. And on the other side, I am saying it is underground cable. See, overhead line conductors, we have something like this. This is A conductor, and this is B, and this was a phase C conductor. Like this, we have three conductors: phase A, phase B, phase C. In case of cable, also we have three conductors. But on the surface of the three conductors, we will be keeping insulation that we are keeping in a closed casing. Now, let me show that. This is that outer closed casing we have, and then inside this we have conductors like phase A conductor, phase B, and then phase C conductor, right? A, B, C conductors we have like this. And on the surface of this A, B, C conductors, we have this insulation. A special insulation material we are going to keep on the surface of each and every one. Right? This is the insulation or dielectric material. Anything you can call insulation, or you can say that as dielectric material. Okay. Tell me, very simple thing here. Very simple. How will be the distance between the conductors in case of overhead line? How will be the distance between the conductors in case of overhead line? It will be generally in the order of meters, right? Generally, it will be in the order of meters. Maybe let's say it is 6 meters. But how is the distance between the conductors in case of cable? How will be the distance between the conductors in case of cable? It will be in the order of centimeters. That will be in the order of centimeters. So the first and basic difference between the two physically speaking, that is GMD, geometric mean distance. So GMD of the cable is very, very low compared to GMD of the overhead line. All of you getting this word? Simple thing only, simple thing only. So first we are saying here, GMD of the cable was very low compared to the GMD of the overhead transmission line. GMD of the cable is very low compared to GMD of the overhead line. But GMR values may be more or less equal, because I can expect that for same current rating, this conductor radius and this conductor radius both will be equal. Conductor radii will be equal for same current rating. Okay? Yeah. Next thing. See, if GMD is low, what you can say? Already we discussed about these things, but still I am repeating. Already I discussed about these things in case of surge impedance comparison and all. Okay, still I am repeating. Please tell me. If GMD is low, what I can say? I need your response, please. I need your response. Inductance value will be less. Inductance per phase will be less. Good, very good. L per phase of the cable will be less compared to L per phase of the overhead line. Sorry. And capacitance per phase will be greater. C per phase of the cable will be greater compared to C per phase of the overhead line. So let me say this another point. Yeah, I am asking you one very simple question now. How come you know capacitance of cable is greater compared to capacitance of overhead line? One thing already we said, for cable, GMD is a low value. For cable, GMD is low value. For cable, I can say GMD is a low value. That's okay. That's okay. Next thing. Please listen. Please listen. What's the another reason to say capacitance is more for cable? What's the another reason to say that capacitance is more for the cable? Anybody? Capacitance is more for the cable. What's the another reason? Another reason is surrounding dielectric medium, whatever you keep here, that will have the relative permittivity greater than 1. But here we have air as a surrounding medium, which will have epsilon r equals to 1. Yes or no? So surrounding dielectric medium will have the relative permittivity greater than 1. Surrounding dielectric medium will have the relative permittivity greater than 1. Not only that, you observe here, how is the distance between this conductor and ground? In case of cable, how is the distance between the conductor and ground? It's very, very less, na? Distance between the conductor and ground is very, very less. Yes or no? Yes. So in that view, earth effect is very high. That is also one of the reasons to say that the capacitance of cable is greater. High earth effect. You can say this as high earth effect is also one of the reasons to say that capacitance of the cable is greater compared to overhead line. So these are the various reasons. And other comparisons, surge impedance of cable will be less compared to surge impedance of the overhead line. Already we said this one. And surge impedance loading, if you compare of the cable compared to overhead line, that will be greater. SIL will be greater. Okay. And next comparison is velocity of wave propagation is less for cable compared to overhead line. That's also one comparison. If you want, you can make. Yeah, please complete it quickly. Please write it quickly. These are things which we discussed. Just we are reviewing. Okay. We are concluding here. Okay. Velocity of wave propagation in the underground cable will be less compared to velocity of wave propagation in overhead transmission line wire. Next, what is the practical loading on the cable? Practical loadings. All of you, please tell me. Practical loading on cable will be always loading less than SIL. Loading less than SIL, and it is done based on thermal limit. Right? Done based on thermal limit, you can say. Done based on thermal limit. Thermal limit already I discussed. I am not repeating the explanation. What about the overhead line? Practical loading on overhead line. Practical loading on overhead line. On what basis we keep the loading on overhead line? If it is a short line, thermal limit. Short line, It's based on thermal limit, and if it is a medium line, medium length of transmission lines, we keep this on voltage drop limit, and if it's a long length of line, we are keeping it based on steady state stability limit. Okay. Yeah. So all of you getting it? All of you getting? Once you have completed, please raise your hands. I will make the comparison between cable and overhead line with respect to its conductor resistance. Yeah. Yes, good. Just review of the previous things which we have discussed. Okay, please listen now. See, this is a conductor A, let me consider. It will have some resistance of R. Again, this is a conductor we are considering, conductor A. This is having some resistance of R again, R. Okay, so how is the resistance of conductor A in the overhead line? And how is the resistance of conductor A in the cable? All of you listen. Generally, listen, stop right. Generally, resistance is a formula rho L by A. Both are having same length, same cross section area. So both will have same resistance in the view of rho L by A. Okay. But we have some other things which is commanding the resistance value. One is a temperature. So you see, you are keeping these three conductors in case of overhead line in the outside atmosphere. So there is a good cooling provided by means of atmospheric condition, right? Yes or no? But here you see, you are keeping three conductors inside a closed casing. That closed casing we are keeping inside the ground. Yes or no? So that makes the operating temperature of these conductors as very, very high. So because of high operating temperature, definitely resistance of these cable conductors will be greater compared to the overhead line conductors. Okay, so conductor resistance for the cable R per phase, right? Conductor resistance per cable greater compared to R per phase of overhead line. And what's the reason for it? Reason for this, I'm going to say, reason one is cable conductor operates at high temperature. Cable conductor operates at high temperature. Cable conductor operates at high temperature. That's one reason. Next reason, anybody? Next reason, please tell me. Next reason, listen. So we have some other things which is commanding the resistance here. One is the skin effect. Next one is the proximity. Skin effect and proximity effect. Skin effect will be same, more or less both. But we have to discuss a term proximity effect now. Proximity effect. Listen please. Proximity effect, it's a type of mutual effect actually. Proximity effect, it's a type of mutual effect. I will tell you. If two conductors are there, one beside the other. Because of the flux linkages produced by one conductor, there is some EMF induced in the second conductor. Listen carefully. Because of flux linkages produced by conductor number 1, there is some EMF induced in the conductor 2. That EMF may show some opposition for the existing current flow. Else you can say that will create some eddy currents. Those eddy currents will definitely disrupt the current distribution. Eddy currents will be created. Those eddy currents will be definitely disturbing the current distribution. By that way, current distribution may become little non-uniform. Because of that, definitely resistance will be a bit increased because of the proximity effect. All of you getting? Yeah. When this proximity effect is very high, means particularly if the conductor to conductor gap is less, conductor to conductor distance is less. At that time, the proximity effect is more. So in case of cable, the proximity effect is more, that will cause for higher resistance for this conductor. Okay, so more proximity effect in the cable, more proximity effect in the cable, So almost all the technical comparisons we have made, irrespective of economical comparisons, we have done all the technical comparisons between the overhead lines and the cables here. Okay, yeah. Now, from this point onwards, I will be taking up a single core underground cable. Single core means only one conductor. That's meaning. Conductor itself is called as core here. Single core underground cable I will take. I will discuss about what are the various layers we are keeping in the cable construction. That I will discuss. Okay. And then we will move on to, we will be moving on to what we call insulation resistance calculation, capacitance calculation, these things. Okay. Yeah. So let us say single core underground cable construction. Construction of single core UG cable. Construction of the single core underground cable. See, as we said earlier, initially we have a conductor. I'm showing that conductor here. Just observe. This is a conductor, or we can say it as a core or conductor, like this we have. Core or conductor. Or conductor. Next. What type of conductor we have to use here? Material may be aluminum or copper, that depends. Material of this one might be aluminum or might be copper sometimes. That doesn't matter. But now what I am asking is, what type of conductor? Is it a solid conductor or AAC or ACSR? Which one? AAC we have to use to reduce the skin effect and the proximity. We should go for AAC conductor. You no need to go for ACSR. You no need to go for ACSR. So you can go for AAC conductor. Okay. So it is AAC conductor. AAC conductor we have to use. Next. Then on the surface of this AAC conductor, we are going to keep the insulation. Right? So I am showing that the insulation layer, here. Like this, I am showing the insulation layer. Yeah, so this is insulation. Yeah, insulation. Let's take up the insulation part a little bit. Insulation, or sometimes we call it as dielectric material also, no issue, no difference. Right? In our view, there is no difference. Insulation. Tell me please, why do you have to keep that insulation on the surface of conductor? Why do you have to keep that insulation? To reduce the leakage current, to isolate the conductor from ground, Yes or no? Right. To reduce leakage current value. To reduce the leakage current value, we are keeping the insulation on the surface of the conductor. That's one. Next, tell me, what are the properties required for this? And what's the material we are going to use? That is sufficient. What are the properties for this insulation required for the cable? Properties required. Tell me please, what are the properties required? Yes, Naveen. Yes, Naveen. Yeah, tell me, what are the properties? First and foremost property, high dielectric strength. High dielectric strength. Dielectric strength. Okay. High dielectric strength. Sorry. Yeah, high dielectric strength. High dielectric strength. This is one of the necessary property for a insulator. Next one, it will be high resistance. Means high insulation resistance. Generally, this insulation resistance will be in the order of megaohms. Generally, insulation resistance will be in the order of megaohms. Okay. So high insulation resistance or resistivity is a better term even compared to high insulation. Okay, anyhow, I'll write resistance. High insulation resistance. Generally, this resistance will be in the order of megaohms. Okay, next thing. Actually, these two are necessary properties. If these two are there, then only we are going to call it as an insulator. If these two are there, then only we call it as insulator. Okay, next. Some other properties I am going to call for this insulation. See, this material, listen please. This insulation, we are keeping on the surface of conductor. So it will be in touch with the conductor. Because of the high heat produced by the conductor, insulation should not melt down. Because of the high heat produced by the conductor, insulation should not be melt down. Means this insulation should have high thermal stability. You can say it should have high thermal stability. Next one. High thermal conductivity. High thermal conductivity means it should transfer the heat quickly from conductor to outside. High thermal conductivity. High thermal stability, one term we are saying. Next term we are calling as high thermal conductivity. Okay, next property I am going to say for this one. Non-hygroscopic. Non-hygroscopic means it should not absorb any wet content, or you can say water content. Non-hygroscopic means should not absorb any wet content, or you can say water content. Wet content, or you can say water content. Non-hygroscopic. Okay. Next. It should not participate in any electrical or chemical reactions. Means it should be electrically and chemically inactive. Electrically and chemically inactive. Etc. So these are the various properties required for that insulation. Mechanical properties and all, it's okay. Should attach in a proper way, like that we can see. Next thing. What are the materials we are going to use? I'll say materials. Materials used. First one, rubber. Rubber, and next one we can say vulcanized India rubber, VIR. Vulcanized India rubber, VIR. What do you mean by vulcanization? All of you listen. Don't ask me this doubt. Okay, please tell me. What do you mean by vulcanization? Vulcanization means adding sulfur. Adding sulfur. Okay, yeah. Somebody is asking a doubt here. Thermal conductivity means, listen please, Ashish, thermal conductivity. It should be a good heat transfer body. Means the conductor is developing the heat. That heat should be transferred to the outside environment quickly by this insulation medium. So it should have good conductivity, thermal conductivity properties. That's it. Electrically inactive means it should not participate in any electrical reaction with that insulator. Sorry, with that conductor. Yeah, to give strength, yes, good. To give strength to the rubber, we will be adding that sulfur. That process is called as vulcanization. Next one. Next one will be impregnated paper. Impregnated paper. Oil impregnated paper also we'll say sometimes. Next one will be PVC. Polyvinyl chloride. Vinyl. Polyvinyl chloride. PVC. And the last one I'm saying here in this XLPE. XLPE, and this will be cross-linked polythene. Cross-linked polythene, or you can say polyethylene also. Polythene or polyethylene, both will be same. Cross-linked polythene. Okay. Listen, I will keep the dielectric strengths of these materials now. I will keep the dielectric strengths of these materials. Rubber, 30 kV per millimeters. Rubber will have a dielectric strength of 30 kV per millimeter. What is the dielectric strength of air? As a reference, you tell me. What's the dielectric strength of air? 30 kV per centimeter. Na? 30 kV per centimeter. Or you said this one 3 kV per millimeter, right? 3 kV per millimeter. That's for air. For reference, I am saying here. But rubber, how much it will be? 30 kV by millimeter. So 10 times more compared to air. 10 times more compared to air, we can say. Okay? Yeah. Vulcanized in India rubber. Vulcanized in India rubber. After doing the vulcanization, dielectric strength definitely decreases. Dielectric strength definitely decreases. It will be in the range of 10 to 20 kilovolts per millimeter. For the VIR, vulcanized India rubber, dielectric strength will be in the range of 10 to 20 kilovolts per millimeters. Next, impregnated paper will have a strength around 30 kV per millimeter. 30 kV per millimeter impregnated paper. Polyvinyl chloride around 18 kV per millimeter. Polyvinyl chloride around 18 kV per millimeter. And XLPE around 20 kV per millimeters. Around 20 kV per millimeters. These are the dielectric strengths of these materials. Most famously, we are using XLPE. Most famously, we are using XLPE. Almost all practical cables, what I have observed are having an insulation of XLPE, right? Because of its durability. Because of its durability means it will last for a good amount of time. Good life we can achieve with the XLPE. Okay, so let's see. Impregnated paper means just paper mingled with oil. Paper mingled with oil. Okay, yeah. Next, let's move back. Listen, listen. We have taken the conductor first. Conductor. On the conductor, we kept the insulation. Can we keep this construction directly into ground? Can we keep this construction directly into ground? No, because there may be some moisture content in the earth, right? Definitely, because of rain, whatever it is, moisture content in the earth that may enter into the insulation that will decrease its strength, insulation strength. Okay, to avoid the entry of the moisture content, into the insulation, I will be keeping some metallic sheath. I will be keeping this metallic sheath here. Okay, so I'm showing this metallic sheath. Metallic sheath. Metallic sheath. What's the purpose of this metallic sheath here? To avoid the entry of moisture content into the insulation. Let me write quickly. Metallic sheath is to avoid the entry of moisture content into insulation. Moisture content into insulation. Okay, to avoid the entry of the moisture content into insulation. So generally, this metallic sheath is made up of either lead lead sheet, we can say sometimes, or you can say aluminum sheet. Some places the people are using copper also. Some places the people are using copper also, but copper is very costly of usage. So the people are going practically either with a lead or you can say aluminum sheet. Okay, next thing. See, after keeping this metallic sheet, can we keep this into the ground? Can we keep this into the ground? No. Why? In the sense, there is a possibility of getting some corrosion. There is a possibility of getting some corrosion on this metallic sheet. To avoid the corrosion on the metallic sheet, we will be keeping a low-grade insulator. We'll be keeping a low-grade insulator, which is called as bedding layer. We'll be keeping a low-grade insulator here to avoid the corrosion. Avoid the corrosion on this metallic sheet, and this is going to be called as bedding layer. Okay. So the next layer we are naming as bedding is kept to avoid corrosion on metallic sheet. Avoid the corrosion on the metallic sheet. Okay. What is the material we'll be using for bedding here? Material, it's basically a low-grade insulator. Basically, it's a low-grade insulator. Examples for these low-grade insulators will be jute, or we have one more material like Hessian. Right? Jute, or you can say Hessian. We have 3-core cables also. We not only have single core cables, we have 2-core cables, 3-core cables, 3.5 core cables, 4-core cables, like that. Okay, 12 core, 16 core also we have, with various applications, I can say. Let me continue. So we are keeping this bedding layer. Next thing, listen. Whenever we are transporting the cable from company to installation place, right? So while you are doing the transportation, we have to carry the cable into the lorry, and after taking that to the installation place, we have to take it down. So during these things, there may be a chance of getting some mechanical stress on the cable. Because of that mechanical stress, there may be a possibility for damage of the insulation and the conductor. So to protect this insulation and conductor from external mechanical stresses, we are keeping one layer called as armoring mechanical protection layer. We'll keep one layer called as armoring, called as mechanical protection layer. Armoring. So I can say this as mechanical protection. I'll write here. Armoring. So armoring layer is to provide mechanical protection. Mechanical protection. From external mechanical stresses that you know. What are the materials we will be using for this armoring means? Materials for this armoring. It will be galvanized steel. Or you can say layer of steel strands. Galvanized steel, or you can say we will be using layer of steel strands. That's the armoring layer. Then finally, after keeping this armoring layer, if you are again attempting to keep this construction into ground, there may be a possibility of getting some corrosion on the armoring layer. So To avoid that corrosion, again, in the last stage, we will be keeping a low-grade insulator. We'll be keeping a low-grade insulator. This is called as serving. Again, we will be keeping a low-grade insulator, and this is going to be called as serving. Okay, serving layer. So it is again a low-grade insulator. Low-grade insulator. Serving layer. Done? So I think all of you have understood this. All of you have understood this, what I said. Is it clear? So just remember what are the materials we have to use for each and every layer for the view of examination. For the view of examination, what material we are using? Insulation. We said many materials, right? PVC, XLPE, rubber, VAR. Okay, metallic sheet, aluminum or lead, bedding, low-grade insulator, jute or HCl, armoring, galvanized steel or layer of steel strands. Serving, it's a low-grade insulator again, jute or HCl. Fine. Yeah. So next step. See, in this whole cable construction, which layers you are keeping for the purpose of electrical, which layers you are keeping for the purpose of mechanical, which layers you are keeping in the view of electrical, which layers you are keeping in the view of mechanical. Tell me, conductor, electrical or mechanical? Electrical, definitely. Insulation, also electrical to avoid the leakage current, to withstand the stress. Yes or no? Yeah. Please tell me, please tell me. Insulation. Next, sheet. Metallic sheet, is it electrical purpose or mechanical purpose? Mechanical. Yes or no? Mechanical. Yeah. See, from that point onwards, sheet, bedding, armoring, all these things are for the purpose of mechanical only, maybe to avoid the corrosion or to have the mechanical strength, to provide the mechanical strength and all. Electrically speaking, in the discussion of the cables, I should consider only two layers now. One is a conductor. Next one is the insulation. Next one is the insulation. One more thing I will take, that is the sheath. Inner surface of sheath. Inner surface of sheath we are going to consider. Okay? Yeah. All of you getting? So we have to bother about only thickness of the insulation and the conductor right now in the electrical analysis. So now what I am going to take here is cross-sectional view of single core cable. Cross-sectional view of single core cable. Single core cable, exclusively we are writing this one for the electrical analysis. We are writing it for electrical analysis. Okay, yeah. So like this we have. I'll tell you what is that and all. Just observe. And this is a conductor I am showing now. This is a conductor, right? It's a core, you write if you want core. And on the surface of this core, we have the insulation. On the surface of the core, we have the insulation, right? Insulation. Next thing, next. See, whatever the outer circle you have drawn here, that is the inner surface of sheath. Look, please. It is the inner surface of sheath. Inner surface of sheath or inner periphery. Inner surface, or you can say it's the inner periphery of sheath. Inner surface of sheath. Next. Generally, the sheath is connected to ground. The sheath is connected to ground. Sheath is connected to ground. Next, observe. Radius of core is smaller, I am saying. That core is called as inner conductor sometimes. Core is called as inner conductor. Inner conductor. And the sheath is going to be called as outer conductor sometimes. Sheath will be called as outer conductor sometimes. Okay. And the outer conductor radius I am saying as Kepler. That Kepler can also be called as overall radius of the cable, electrical. Kepler can also be called as overall radius of cable, electrical radius. Overall electrical radius of cable. Electrical radius of cable. Okay. Cable. Next. Getting? Next point I'm going to tell you. Next point. So in these thickness of insulation, if you want, you can say this is the thickness of insulation. Sometimes in exam, they will give thickness of insulation. They will give the thickness of the insulation. I am calling it is T. So you can have that relation here. Kepler equals to smaller plus T. Smaller. Okay. Smaller plus T equals to Kepler. Like that you can see. Smaller plus T equals to Kepler, where T is the thickness of the insulation. T is the thickness of the insulation. Next, let's think in this manner now. Let's think in this. Particularly in cables, we are concentrating only on few topics. First one, calculation of insulation resistance of the cable. Calculation of insulation resistance of cable. That's first one. Second one, calculation of capacitance of single core cable. Right? I'm checking the electric field intensity at each and every point in the cable cross section. Electric field intensity in each and every point in the cable cross section. Capacitance of single core cable. These are some topics we discuss in the single core cables. Then we'll move to 3-core cable for 3-phase supply. 3-core cable will take. And in the 3-core cable, we will be concentrating mainly on the capacitance calculation. Capacitance calculation of the 3-core cable we will be discussing. Okay, then we will see what are the various losses in the cable, and finally we will go with the comparison between the AC cable and the DC cable. Finally, we go with the comparison between AC and the DC cables. Only these topics we are going to limit in the underground cables. Yeah, first topic in this, what we said earlier, that is calculation of insulation resistance of the cable. Insulation resistance of single core cable. Single core cable. Insulation resistance of a single core cable. Okay. All of you listen. All of you listen. See, this is a cross-sectional view of cable, right? And cut view of the cable. Now I am going to think that cable in a longitudinal view. In a longitudinal view, we are going to just have a look. So I'm showing a conductor first. This is a conductor I am showing. Conductor. One wire I have shown. I have to show the other. Okay, yeah. Look, please. This is a conductor, or you can say core, whatever it is. It's a conductor, or you can say core. On the surface of core, we have the insulation. On the surface of the core, we have the insulation. I have the insulation on the upper surface as well as bottom surface also. But for my convenience, I am showing the insulation only in the bottom surface. Okay. I am showing that insulation only in the bottom surface for our convenience only. In this diagram, physically speaking, we have the insulation on the upper as well as lower, both. Right? It is the insulation. And this is a sheath, sheath which is connected to ground. Of course. And this is connected to ground at various places. Okay. Length of this cable is L. Length of this cable is L, I am saying. Length of the cable is L. Yeah, length of the cable is. Next thing. See, this cable, we are going to apply a DC voltage on one side, showing that DC voltage on this side. DC voltage we are keeping. On the other side, I will keep a resistive load, of course. It is a load resistance. Very simple point what I'm going to discuss now. Very, very simple point we are going to discuss. This is DC cable. This is DC cable if you want to consider it. No issue. Very simple point. See, for this cable of length L, one side we have a DC supply, other side we have a load. How is the direction of the current flow in the conductor? In the core, you tell me please. In the core, how is the direction of current flow? Direction of current flow. Definitely this current, this conductor current will be flowing from voltage source to load only. Voltage source to load. That's the direction of the current flow. So this is the direction of the conductor current, core current. Core current, I core. I core. But there will be some current in the insulation also, na? There will be some current in the insulation also. You please tell me now. You please tell me, how is the current direction in the insulation? Direction of current in the insulation. Simple, simple. See, this conductor is operating at a voltage V and sheath is operating at a potential of 0. So we have a current flow from conductor to sheath. Conductor to sheath, we have the current flow. Okay. So we have the direction of the current in this manner. In this manner, we have the direction of the current flow, and this we will call as a leakage current. That we are calling as leakage current. Leakage current. Okay, next. Listen, please. Very simple words I am saying. See, whenever we have some current flow, in certain direction, there is some opposition shown for the current flow, right? Whenever we have a current flow in certain direction, there is some opposition shown for the current flow. Who is going to show that opposition for current flow? Resistivity property, you can call. So that opposition we should show in the equivalent circuit, right? That opposition we should show in the equivalent circuit. Yes or no? Yes, right. So that, see this. So if the current is flowing in this particular direction, there is some opposition shown for this current flow by means of this conductor resistance. By means of the conductor resistance. All of you getting it? Conductor resistance. So that's why in network analysis also you might have discussed it. If current is flowing in this direction, voltage drop might be shown in the opposite direction to that. Voltage drop might be shown in opposite direction to the current flow. Okay. Yeah, like that, not only one, we have many core resistances distributed like this. Many core resistances distributed something like this. R core. Conductor resistances. Okay, next one. Insulation. We have leakage current flow, na? We have leakage current flow. So we have that resistance kept in the direction of current flow only, but our voltage in opposite. So I am showing that insulation resistance between the conductor and sheath. Between the conductor and something like this. These are the insulation resistances we have kept. Insulation resistances we kept. Okay. Very simple question I am asking. Very simple question. Very simple question. Of course, first, before asking the question, I will tell you, is it a distributed model of cable? All of you please tell me. Is it a distributed model of the cable? Yes or no? Yes, it's a distributed model of cable, but for DC supply. Okay. Distributed model of HVDC cable at steady state. Okay, you tell me please. If length of cable is increasing, what will happen to R core? If length of cable is increasing, what will happen to R core? Tell me please. What will happen to R core? Definitely increases, right? Because some more resistance will be added in series. If length of cable is increasing, some more resistance will be added in series with the R core. So overall core resistance, our conductor resistance is going to be increased. So I can say as length of cable is increasing, conductor resistance will increase because it's a series addition. It's a series addition. What will happen to insulation resistance now? What will happen to insulation resistance? Increases or decreases? Insulation resistance. Anybody? Decreases. Why? Because if length is increasing, some more resistance will add in parallel. Some more resistance will add in parallel. So overall insulation resistance is going to be decreased. Insulation resistance will be decreased. So I can say conductor resistance will be proportional to length of cable. Insulation resistance can be inversely proportional to length of the cable. Can we write this statement? Can we write this statement? Yes or no? Yes? Yeah. Core resistance is proportional to length of cable. Insulation resistance will be inversely proportional to length of the cable. Now let's take up the cross-sectional view of cable what we have discussed. And I will show what is the core resistance formula for that. We know already. And what is the insulation resistance for that. So this is the cross-sectional view of the single core cable we have taken. This one. See this. See this core what we said here. It will have a resistivity. Core will have a resistivity of rho core. This insulation will have a resistivity of rho insulation. Insulation will have a resistivity of rho insulation. Okay. First, core resistance I will write. Core or conductor resistance, very simple. Conductor resistance I'm writing. So R core formula will be rho core into length by area of cross section of conductor. Area of cross section of conductor, that area of cross section is pi r square, where smaller is the radius of the core. Right? If the skin effect and proximity effect are there, we have to take up that multiplication. We have to take the multiplication factor. Okay, like 1.6 or 1.7, whatever it is. Leave it aside. Conductor resistance is rho L by A, this formula. Now, listen all of you. L is the length of cable. L is the length of cable. Now we should think about this insulation resistance here. All of you please look here. All of you please. We should think about the insulation resistance now. Insulation resistance. Insulation resistance means we should cover two things here. We should cover two things. One, length of the cable. Length of cable, complete length. Next one, insulation spread between smaller and capital. Insulation was spread between smaller and capital. If you cover these two things, we will get the formula for the insulation resistance. All of you getting my words? Just look at the insulation presence, insulation material presence. It is appearing for total length of the cable. One thing. Next one, it is in between smaller and capital. In this region, we have the resistance. Sorry, insulation. So we have to cover those two things. Okay. So let me take up. In this insulation area, I am considering a circle of x radius. Considering a circle of x radius. Just look here. Considering a circle of x radius. So in and around that x, we are considering a small thickness dx. This is the dx thickness we are considering. I'll write here. A circle of x radius circle. L length will be L length. dx thickness was considered. dx thickness was considered. A circle of x radius, L length, dx thickness was considered. So I think all of you getting it. First, what you do is you try to write resistance of this small portion what you have considered in the insulation. Try to write the resistance formula for this small portion. Then we will think about the resistance of the whole insulation body. Resistance of the whole insulation body. Okay, yeah. So let's say here. So I'm writing in the next slide. So insulation resistance of the thickness what you have considered dr insulation. Dr insulation. So generally, you know, resistance formula is rho L by A. Na? All of you look here, please. All of you look here. Resistance formula will be rho L by A. That's the formula. What is rho? Rho insulation, we should say. What is A here? What is A? Anybody? What's A? Area of cross section through which current is passing out. Area of cross section through which current is passing out. First, you tell me this one. Our area measured perpendicular to direction of current. Area through which current is passing out. Else you can say area measured perpendicular to the direction of the current. Very simple question. Very simple question. Kindly observe. Kindly observe. In this insulation, in which direction we have the current? In this insulation, in which direction we have the current? Is it horizontal to screen or vertical to screen? In this insulation, how is the direction of the current flow? Is it horizontal to the screen or vertical to the screen? Anybody? It is vertical. Sorry, horizontal, not vertical. Horizontal, no. Because you know the insulation current is flowing from core to sheath, right? Insulation current is flowing from core to sheath. Now, this is the direction of the current flow. All of you getting? This is the direction of the current flow. Okay. So after taking this direction of current flow, we should measure the area perpendicular to it. Perpendicular means into the screen, we should take up the area. Into the screen, we should take up the area. Yes? You want me to highlight that X radius portion. X radius portion. It may come simply like this. That X radius portion we have to consider. It may come simply like this. X radius portion. X radius. And length is L. Length is L. Look here, please. Look here, please. Current, whatever the insulation current we talk now, that will be radially outward from this hollow portion. Current will be radially outward here. Current will be radially outward from the surface of this. From the surface of that, current will be radially outward. From how much amount of area the current is coming out now? From how much area the current is coming out? 2 pi x is a perimeter of circle. 2 pi x is a perimeter of circle multiplied with length. Multiplied with length. So it will be 2 pi x L, you can say. Area is 2 pi x into L. That is the area from which the current is leaving. Current is leaving. Okay. What is it L? What's it L? Length of current flow. How much length we have the current flow here? That is the length dx. That's the length as dx. Okay. So this multiplied with dx, you can say that is a dr insulation. That is a dr insulation. dr insulation. So now simply you take the integration. Starting from x equals to small r to x equal to capital R. Starting from x equal to small r to x equal to capital R, you take the integration. By that way, we are going to get the total insulation resistance of the cable. Total insulation resistance of the cable. Right? So I'll write here total R insulation value. Total R insulation value. So R insulation will be equal to integral of dr insulation starting from x equals to small r to capital. So you can write now integral x equal to small r to capital R dr insulation will be O insulation by 2 by xl with respect to x. 2 by xl with respect to xl. So you can write now rho insulation by 2 by L, rho insulation by 2 by L. 1 by x integration is natural logarithm of x. And we should keep the limits from small r to capital R here. Okay, do that quickly. Yeah, so I'm repeating it. Just listen. Either formula for the resistance is rho L by A. That you know. Rho in the sense resistivity of insulation. Area of cross section is area measured perpendicular to direction of the current flow. Area measured perpendicular to the direction of the current flow. If you see in the insulation portion, current is flowing from conductor to sheet in this direction, given in this direction. So we should measure the area perpendicular to this. Perpendicular to this means into the screen we have to check. So if you take up the area from which the current is leaving out, if you take the area from which the current is leaving out, we have a portion in this manner. We have a portion in this manner. Current is leaving out from the surface. Current is leaving out from the surface. From how much area that current is coming out means circle perimeter of the circle 2 pi x multiplied with the length. That is that surface area from which the current is coming. So we have taken up 2 pi x into L as the area of cross section through which current is passing out. And we have L there multiplied with it. L in the sense length of current flow. That length of current flow is nothing but this dx portion, because this is a portion from which the current is leaving out according to our view. So I can say dx. And we have to find out the total insulation resistance. So we should integrate it starting from small r to capital. That's what we are doing. Okay, yeah. So let's say after doing this integration, R insulation will come as rho insulation by 2 by L. After applying limits, you can get it as ln of capital R by small r. Ln of capital R by small r. R insulation equals to rho insulation by 2 by L into ln of capital R by small r. And from this, it is very clear to say that the insulation resistance is inversely proportional to length of the cable. And already in the core resistance, we said R core is proportional to length of the cable. R core is proportional to length of the cable. Okay. Yeah. Next. Tell me what will happen to these two resistance values, R insulation and R core, with respect to length. Means if the length of the cable is increasing, what will happen to these numbers? We know it. R insulation is decreasing, core resistance is increasing. That's okay. Temperature we tell with respect to temperature. If operating temperature increases, if the operating temperature is increasing, tell me please, what will happen to core resistance? What will happen to core resistance if operating temperature is increases, because conductors will have positive temperature coefficient. Okay, core resistance will increase because conductors have positive temperature coefficient. Positive temperature coefficient of resistance. Okay. Positive temperature coefficient of resistance. What about the insulation resistance? Anybody? Tell me, what about the insulation resistance? Insulation resistance will decrease because insulators have negative temperature coefficient of resistance. Insulators will have negative temperature coefficient of resistance. So these are the variations in the core resistance and insulation resistance with respect to temperature. Okay. So next we'll take up one small problem on this one. Small problem on this resistances. So we look at this. It's a very simple question. Very, very simple question. Just go through it. Yeah. So a underground cable has the per kilometer core and insulation resistances as 0.5 ohms and 50 mega ohm respectively. 0.5 ohm is a series resistance and insulation resistance is 50 mega ohm, that is shunt resistance. What are these values for 5 kilometer length of the same cable? Means what will be the core resistance and insulation resistance for 5 kilometer length of the same cable? All of you. See, for 1 kilometer length, I'll say core resistance R core 1.5 ohms. And whereas the insulation resistance is said as 5 mega ohms and 50 mega ohm. 50 mega ohm. And for a length of 5 kilometers, what will happen? So you consider this as L1 length and you consider this as L2 length. Huh? R4 is proportional to length of cable. Na? So R4 2 equals to R4 1 into L2 by L1 because it is proportional to length of cable. R4 is proportional to length of the cable. So you can get R4 1 that is 0.5 and L2 by L1 is 5. So it will be 2.5 ohms is a core resistance. 2.5 ohms is a core resistance. Whereas if you see insulation resistance is inversely proportional to length of the cable. So R insulation 2 equals to R insulation 1 into L1 by L2. L1 by L2. So R insulation is proportional to 1 by length. Means you can call R insulation into length is constant. R insulation into length is constant. So R insulation 1 into length 1. R insulation 2 into length 2. These two are constant. So R insulation 2 will come like this. So you can write now R insulation 2 will be equals to R insulation 1, 50 mega ohm, and it is 1 by 5. Become like 10 mega ohms. That R insulation 2 will come like 10 mega ohms. Clear, simple, very simple problem. Very, very simple problem. Okay, I think it is sufficient for the conductor resistance and the insulation resistance. So only one thing we have to remember all the time. Conductor resistance is a series resistance. Insulation resistance is a shunt resistance of the model. So series resistance, it was a shunt resistance of the model. Yeah, next. Let's continue. The next topic, what we are going to discuss in the single core cables is electric field distribution. Electric field distribution in the cable or electrostatic stress distribution in the cable. Electrostatic stress distribution in the single core cable. Electrostatic stress distribution in the single core cable. See, this electrostatic stress can also be called as electric field intensity. Electric field intensity, you can say, right? Electrostatic stress can also be called as electric field intensity. Else you can say voltage gradient. Various names are there for this. Voltage gradient, you can say, or you can call this one potential gradient also. Potential gradient. Okay, all these terms are seen. Electric field intensity, or you can say voltage gradient, or you can say potential gradient, or you can call that as electrostatic stress. See, listen all of you. In order to find out that electrostatic stress, the given conductor has to be represented in some charge distribution form. The given conductor has to be represented in some form of charge distribution, like we have done in the overhead line. Overhead line we represented as a line charge, right? Overhead line we represent as a line charge. Cable, conductor, core also represented as a line charge only. Core of the cable also represented as a line charge. For example, I have a line charge like plus Q coulomb per meter. I have a line charge of plus Q coulomb per meter, line charge. Line charge. Beside that line charge, I am staying at some point X. Beside to that line charge, I am staying at a point X. This point X is at a distance of X from the line charge, obviously. The point X is at a distance of X from the line charge. Okay. Tell me, what is the electric field intensity at this place X? Formula for the electric field intensity at this point X. Anybody? Already we discussed. I think first class only we have done this. What's the formula? Is it Q by 2 pi epsilon X? I can write Q by 2 pi epsilon into X. That is a field intensity at a point X beside the line charge. Q by 2 pi epsilon into X. This formula we are going to utilize to find out the field intensity in the cable cross section. Find out the field intensity in the cable cross section. Okay, yeah. See, for example, this is a cable what we have now. This is a cable. This is a cable. Yeah, listen please. So at some point X, we are standing here, which is at a distance of X from the line charge, X. At all the points on this X radius circle, if you consider, if you want, take a circle of X radius, this X radius. At all the points on the circle, what is the field intensity means? It will be Q by 2 pi epsilon X only, na? Because this core, what you said, might have a charge of Q operating at a voltage of V with respect to ground. That is operating at a voltage of V, and charge on this core is Q. Right. Due to this Q, the field intensity at this point X will be Q by 2 pi epsilon into X. Not only at this point, at all the points on the circle of X radius will have the field intensity Q by 2 pi epsilon into X. So I think all of you getting it. Can I write it now? So at any point X in the cable cross section, electric field intensity will be Q by 2 pi epsilon into X. By 2 pi epsilon into X. Clear? Q by 2 pi epsilon into X. What is the field intensity on the conductor surface? Anybody? What is the field intensity on the conductor surface? Tell me please. That will be Q by 2 pi epsilon into smaller, because at X I will replace radius of the tube. That's it. Okay. So on the core surface or conductor surface, you have to replace that X with smaller, so that electric field intensity will come to be Q by 2 pi epsilon into smaller. Q by 2 pi epsilon into smaller. X equals to smaller. Next, on the sheet, you have to keep X equals to capital R. On the sheet means outer conductor, right? Outer conductor. You have to keep that X equal to capital R. X you should move to surface of the sheet. Now, what will happen to that? That will be E capital R here. Now, Q by 2 pi epsilon into capital Q by 2 pi epsilon into capital. Yeah, Q is a line charge density already I said. So we got at any point X in the cable cross section on the surface of core as well as on the surface of sheath also. What is field intensity inside the core? What is the field intensity inside the core? Already I discussed in the discussion of the, I think, bundle conductors, right? Just recalling all the things what we have discussed. So inside the core, electric field intensity value was 0. Electric field intensity value 0. So I'm sorry, I'm really sorry. Yeah. So let's continue like this. Inside the core, you said it's 0. Just I will ask in a sequence. Just tell me. What's the field intensity inside the core? 0. Okay. On the core surface, Q by 2 pi epsilon to smaller. Q by 2 pi epsilon to smaller. Starting from core to sheath, at any point you want to measure, you go with an equation Q by 2 pi epsilon into X. Means whatever the equation we have written Q by 2 pi epsilon into X is valid only for X less than smaller. Sorry, X greater than smaller. Is valid only for X greater than smaller. Whereas for X less than smaller, electric field intensity will be 0. X less than smaller, electric field intensity value will be 0. Whereas on the sheath surface, we have to keep X equals to capital R. So you get Q by 2 pi epsilon to capital. Are you fulfilling this heading requirement? What's the heading we have given? Are you capable to fulfill the heading requirement here? What's the heading requirement? Yeah, tell me please. Nobody is responding. What happened? Yeah, please kindly respond. What is the heading we have given? electrostatic stress distribution throughout the cross section of the cable. That is satisfied, right? We got the field intensity at all the places. Electrostatic stress is nothing but electric field intensity only, na? Okay, but the problem here is, I'll tell you, the problem here is we are getting the field intensity in terms of Q, charge, in terms of charge. But what you know generally for this conductor, is it the applied voltage or charge? But you know generally for the conductor, is it the applied voltage or charge? Applied voltage you know rather than charge. So now you try to find out a relationship between this charge and voltage. A relationship between this charge and voltage, that by using that relationship, we will be going with that field intensities in terms of voltage. In terms of voltage. Okay? With that aim, we have to work. Listen. Taking an example, simple example, very simple example. Don't confuse, and don't complicate it. Think as a simple view. Simple. This is one dielectric material. Dielectric material we have. Every dielectric. One side we have A, I'll say. Other side, I'll say we have a point. One side we have A, other side we have B. Point. Now, listen now. See, this dielectric, I am cutting into number of sections. Each and every section 1 centimeter you assume. Each and every section is 1 centimeter. 1 centimeter. For each section, dielectric strength is 20 kV per centimeter. For each 1 centimeter section, dielectric strength is 20 kV per centimeter. What's the meaning of that? What's the meaning of that 20 kV per centimeter here? Dielectric strength of each section is 20 kV per centimeter. What's the meaning of that? Means in 1 centimeter gap, there is a potential of 20 kV. In 1 centimeter, there is a potential gap of 20 kV. All of you getting it? Yes or no? I need your answer for this. 20 kV per centimeter means in 1 centimeter, there is a potential gap of 20 centimeters. Okay, done. Next. Like that. For each and every section, I will give the value of electric field intensity. For each and every section, I will give the value of electric field intensity. Now, if you sum up all these electric field intensities, what it will give? If I sum up all those electric field intensities, what it will give? Voltage between A and B, na? Summation of electric field intensities is nothing but voltage between A and B. All of you getting it? Voltage between A and B is nothing but sum of all electric field intensities between A and B. Sum of all electric field intensities between A and B. In the same way, voltage from core to sheath, you see. Voltage from this core to sheath is V. That is nothing but summation of all electric field intensities starting from core to sheath. In the similar way, voltage from core to sheath will be equal to sum of electric field intensities from core to sheath. Sum of the electric field intensities from the core to sheath. Yeah, next thing. See, voltage from core to sheath is V here. Voltage from core to sheath is V. What do you mean by summation? Integration. Summation means integration. Integration of what? Electric field intensity with respect to X. Integration of electric field intensity with respect to X. Starting from which point to which point? Small r to capital R issues. Starting from small r to capital. X equal to small r to capital. Now you can write here x equal to small r to capital R. What is it Ex value? Already we got q by 2 pi epsilon x is a Ex value. Q by 2 pi epsilon x is the Ex value. So with respect to x. With respect to x. Now you do that integration. You take q by 2 pi epsilon out and you have 1 by x integration. We'll get it some value. So let's say voltage V equals to integral x equal to smaller to, yeah. After doing integration, I will take directly q by 2 pi epsilon and 1 by x integration is natural logarithm of x here. X we have to take the limits from smaller to capital. And if you apply the limits, you will be getting here q by 2 pi epsilon into natural logarithm capital R by small r. This is a voltage. Voltage V equals to q by 2 pi epsilon ln of capital R by small r. Why we are discussing these things? Why we are discussing about these things? Tell me please, anybody? We know the field intensity at all the places by using these equations, right? We know the field intensity at all the places in the cable by using these equations. Again, why you are discussing this? Means we are getting the field intensity in terms of charge that you have to replace in terms of voltage. That you have to replace in terms of voltage. For that purpose, we have done. Ultimately, we got the relation between charge and voltage here. What is the charge here? Q. That is 2 pi epsilon into voltage by natural logarithm capital R by small r. Natural logarithm capital R by small r. That you substitute in the Ex equation. Ex, electric field intensity at any point x. Okay. So at any point x in the, at any point x in the cable cross section, Ex equals to, we know already it is q by 2 pi epsilon into x here, and that q we replace with 2 pi epsilon into voltage by natural logarithm capital R by small r into 1 by 2 pi epsilon into x. 1 by 2 pi epsilon into x. And the 2 pi epsilon will be cancelled out. And you will be getting it like v by x into ln of capital R by small r. V by x into ln of capital R by small r. That is the expression for electric field intensity at any point x. At any point x. V by x into ln of capital R by. Now you replace that x with small r. You will get the field intensity on the core. You replace x with capital R. You get the field intensity of the sheet. Okay, yeah. So let's show in the next slide. Next slide. Yeah, please complete it if you are writing still. Please complete this one quickly. Okay, done. So on the core surface, if you write on the core surface means x equal to small r. Electric field intensity will be V by small r into ln of capital R by small r. On the sheet surface, means you should keep x equal to capital R here. Field intensity will be equal to V by capital R into ln of capital R by small r. V capital R equals to V by capital R into ln of capital R by small r. Like this, you will get the field intensity. Field intensity on the core we get and field intensity on the sheet. Yeah. So I'm showing previous slides. 20F, somebody is asking 20F is completed. 20F. Okay, yeah. Next. Let's compare this E smaller and E capital R values. Let's compare this E smaller and E capital R. So take up this ratio E smaller and E capital R. What you get now? E small r by E capital R. That will come to be capital R by small r. E small r by E capital R. We are going to get like capital R by small r. Yes or no? Of course, this value was greater than 1 definitely. Capital R by small r value is definitely greater than 1. Means observation is that E small r is greater compared to E capital R. E small r is greater compared to E capital. What's the meaning of this? What's the meaning of this? So maximum electrostatic stress occurs on the surface of the core. Maximum electrostatic stress occurs on the surface of the core, whereas on the surface of sheath, we get the minimum electrostatic stress. Minimum electrostatic stress. But you should think in a clear-cut way. All of you listen, stop writing. All of you listen, stop writing. See, on the surface of core, we have the maximum field intensity. Nearby the sheath, we have the minimum field intensity. That's okay. That's okay. Who is experiencing the stress? You are saying the term stress, right? Stress. Who is experiencing the stress? Anybody? Who is experiencing the stress? Insulation. Insulator. Insulator is the thing who is experiencing the stress, right? Means whatever the dielectric material you kept between core and sheath, it experiences higher stress nearby the conductor, lower stress nearby the sheath. That's the meaning. All of you understood this meaning? So we have the maximum field intensity on the core surface and minimum field intensity on the sheath surface means dielectric material experiences maximum stress nearby core and minimum stress nearby sheath. Minimum stress nearby sheath. Maximum stress nearby the core, minimum stress nearby the sheath. Okay? That's the meaning. Now we will see how is that distribution of field intensity in the dielectric material, starting from core surface to sheath. How is that electric field intensity distribution? That we'll see. So just have a look here. I'm taking a plot with x-axis and y-axis like this, right? So like this here. See this? It's a field intensity, and it's a point x. Now we should take up this field distribution starting from core surface to the sheath. Core surface to sheath we have to take up. Sheath. Okay, next thing. On the core we have the maximum field intensity. On the sheath we have the minimum field intensity. We said. On the core we have the maximum field intensity like this. E smaller, maximum value. And on the sheet, we have some minimum field intensity like this. I'm showing here. This is E capital. E capital. Okay, fine. How is it variation in the field intensity starting from core to sheet? How is that variation in the field intensity starting from core to sheet? Is it linear variation or non-linear variation? Definitely non-linear. Why it is so means, you know that Ex is inversely proportional to X, right? Ex is inversely proportional to X. So that we have a non-linear variation for this field intensity starting from core surface to sheet. Get a non-linear variation in the field intensity. Non-linear field distribution. So else you can say rectangular hyperbola. Else you can say we have a non-uniform distribution of field intensity, or the dielectric material what you kept between core and sheath, it was non-uniformly stressed. Okay, so there is a non-uniform stress distribution. Non-uniform stress distribution. in the cable cross section. Non-uniform stress distribution in the cable cross section. Okay, right. So have a break for 5 minutes. So after break, we'll discuss little more about this field intensity. Then we will move on to capacitance of the single loop. So 5 minutes break. So I have resumed the audio video on screen. So now, see why we are doing all these calculations means electric field intensity. Why you are calculating it? That we should know first. Look here, please. Look here. See, the reason of calculating this electric field intensity is simply to select the material dielectric strength. To select the dielectric material strength. For that purpose, we are doing it. See, generally, the dielectric material strength we should select based on the highest value of the field intensity. Based on the highest value of field intensity. Where we are getting the highest value of field intensity? On the core surface, we are getting it. On the core surface, we are getting it. Yes or no? Right. Fine. See this one. See, so you calculate this electric field intensity is smaller value, and you multiply that with some factor, maybe 2 or 2.5 safety factor, and then based on that you select the material. With that material, we should construct the cable. Right? So in order to reduce the cost of the cable, we should reduce the cost of the insulation. We have to reduce the cost of insulation. To reduce the cost of insulation, we should reduce the value of E smaller. Then E smaller depends upon what quantities? E smaller value depends on what quantities here? E smaller depends upon operating voltage, smaller Kepler value. Okay. Now let me assume that operating voltage remains constant. And Kepler value, so-called overall radius of cable, also constant. Now you consider the smaller as a variable, and you try to find out that smaller value in order to minimize this field intensity. That we are going to name it as most economical radius of the core or most economical size of the cable. I will explain again point by point. Just to take this heading first. Most economical size of cable, or you can call most economical radius of core. Most economical size of cable, or you can say most economical radius of core. What's the purpose of this one? What's the aim of this? To minimize cost of insulation. How to minimize the cost of insulation? Minimizing E smaller value. By taking operating voltage and capital R as constants. Kindly observe. I am saying you again. We have to minimize the cost of insulation to reduce the cost of cable. Okay. For that purpose, we are minimizing the E smaller value. So to minimize the E smaller value, we should think E smaller depends upon three quantities. One is operating voltage, next one overall radius of cable, next one is a smaller value. Now we are keeping this capital V and capital R as constants. Now we are going to check for the smaller variation. Okay. Listen. So already I said E smaller formula V by smaller into ln of capital R by smaller. V by smaller into ln of capital R by smaller, you can say. Right. See, minimizing E smaller is nothing but maximizing denominator. Minimizing E smaller value is nothing but maximizing the denominator. Minimizing E smaller is nothing but maximizing the denominator. See, maximizing the denominator means we should take up the differential quantity of this one as 0. Means d by dr smaller. D by d smaller of this should be equals to 0. By doing the differentiation, we should get that relationship. Okay. Yeah. So let's write now. So d by d small r of small r into ln of capital R by small r is equal to 0. D by d small r of small r into ln of capital R by small r is equal to 0. Okay, take up the differentiation. Take up the differentiation and do your differentiation, and finally, the final result what you are going to expect here is capital R by small r equals to E. Do the differentiation later. Do the differentiation later. Ultimately, the final condition what you can expect is capital R by small r equals to small e. The small e number is 2.718. 2.718. In reverse, you can call small r by capital R is 1 by e. That 1 by e number is 0.368. Then, what is radius of core you can get? 0.368 times of capital R. 0.368 times of capital R. So, this is called as most economical radius of the core. Called as most economical radius of the core. Economical radius of core. Small r equals to 0.368 into capital R. That is going to be called as most economical radius of core. Most economical radius of. Now, you please listen. With this most economical radius of core, you find out what is electric field intensity on the core surface, what is electric field intensity on the sheet. Okay, simple. Let me write. With that most economical radius of core, I'll write here only. With most economical radius of core, with small r by capital R equals to 0.368 condition. 0.368 condition. First one, on the core. What is field intensity? You can say. What is field intensity? Formula V by smaller. Listen please. Smaller. That smaller you should replace with 0.368 into capital R. Smaller you should replace with 0.368 into capital R. Into natural logarithm. Capital R by smaller is E. Capital R by smaller value E. Ln of E 1. You can get this like V by 0.368 times of capital. V by 0.368 times of capital. That is a electric field intensity on the core surface with the most economical radius condition. Next, on the sheet, how it is? On the sheet. Next one is on the sheet with most economical radius condition. E capital R. So it is V by capital R into ln of condition is capital R by small r equals to E. So it will come as V by capital R. V by capital R. Like this, you get the field intensities on the core surface as well as on the sheet surface with the most economical radius condition. The most economical radius condition. Yeah. So I think all of you getting it. Is this clear for all? Ashwini, it is a UV differentiation, no? It's a UV differentiation, U dash into V plus V into U dash. That differentiation you have to do. Sir, will this be the actual radius of core that will be present in the UG cables? Yeah, actually, not getting final answer. Which answer? This one, capital R by small r equals to E. This one. So you do differentiation. So first you should take differentiation of small r with respect to R1 you get. So you get ln of capital R by small r, and you have plus capital R, so small r into ln of capital R by small r. Differentiation will be ln of x differentiation 1 by x. So 1 by capital R by small r. Like that you should do. Let me write one step. You get 1 into ln of capital R by small r, u dash into v plus v into u dash. 1 by capital R by small r into, and this capital R by small r again differentiated means minus capital R by small r square equals to 0. You do this. you can see this whole will come -1. This whole product will come -1. That you send to other side, it will come +1. So ln of capital R by small r is 1. ln of capital R by small r is 1. Then you get capital R by small r equals to E. Like that. Next, let's continue. Let's continue. Yeah. Capital R by small r is E only, na? Good, Aishwarya. Good. Getting good. Let's continue. Let's continue. So I'm taking up a different plot here. I'm taking up a different plot. Different plot means earlier, we have taken the field intensity variation starting from core to sheet. Starting from core to sheet, we have taken. But now, I'm taking up variation in the field intensity on the core surface only. Variation in the field intensity on the core surface only. Only core surface I am taking with respect to small r by capital R. Variation in the field intensity on the core with respect to small r by capital R variation. Not throughout the length. Not throughout the length. Only core surface. With respect to different dimensions of the cable. With respect to different dimensions of the cable. If you do that, if you plot this one, you will be getting a plot something like this. Something like this, you will get a plot. All of you getting? I am not saying you exactly how this is coming at all. This is a plot which we can expect. ER with respect to small r by capital. Now you see. This is the minimum field intensity we can experience on the core surface. Lowest field intensity we can experience on the core surface. That's what we have just now. We got V by 0.368 into capital R. V by 0.368 into capital R. That's the lowest field intensity which we can experience on the core surface for any dimension of the cable. This value V by 0.368 times. Okay, then done. Next. For what condition we are getting that? For what condition we are getting that? For a condition of small r by capital R equals to 0.368. For a condition of 0.368, we are getting it. Okay, next. See, till now, what we thought is, go for most economical radius of cable. You will get the lowest field intensity like this number. Like this number you will get. And you multiply this with a factor of multiplication, maybe say 2. Okay. We'll get some value of field intensity resulted. With that value, you select the material and you construct the cable with respect to that. So that cost of cable will be minimized. That's what we said. Now, practically speaking, is it preferable to consider or not? Is it preferable to design the cable with the most economical radius or not? That's the thing we have to discuss. Practically speaking, is it preferable to design the cable with the most economical size or not? Okay, listen please, listen kindly. For example, all of you stop writing. Just look what I am saying. Just look. For example, this is a cable we are having. Okay. This is a cable we have. I have designed this cable. This is smaller capital. I have designed this cable with smaller by capital exactly 0.368. All of you listen to me. Stop writing. It's a very simple concept. Don't complicate. I have designed the cable with a dimension of 0.368. Fine. Means with respect to that, I found the field intensity on the core surface and I multiplied that with some safety factor, selected the dielectric material based on that. That dielectric material we kept in between core and sheet. Well, unfortunately, a switching surge occurred. Switching surge occurred on the cable. Because of that switching surge, there is a rise in the operating voltage as well as there is a rise in the electric field intensity of the conductor also. Because of that, unfortunately, some ionization or you can say corona happened on the conductor surface like this. The resultant electric field intensity what we got because of the switching surge, high electric field intensity was created. Because of the field intensity, we have some corona on the conductor surface or you can say ionization on the conductor surface. Yeah, look here. If corona occurs due to some reason, whatever it is. See, listen, corona is occurring means surrounding dielectric medium of the core gets ionized, right? Surrounding dielectric medium of the core is getting ionized. Means can I say that that particular dielectric medium converted into conducting material. That particular dielectric medium converted into conducting material. Yes or no? Yes or no? If it's getting ionized means the dielectric medium what we have there, it is getting converted into conducting medium. Conducting medium. Okay, fine. Okay. See, if it is getting converted into conducting medium, what will happen to smaller? What will happen to overall radius of cable? Sir, conductor, smaller value will definitely increase. Na? Smaller value will definitely increase. Okay. What about Kepler value? Smaller value increase, that's okay. Smaller value was increased. What about the value of Kepler? What about the value of Kepler? Kepler remains same. Overall radius of cable will be remains same, right? So Kepler remains same. Getting me? Smaller value was increased and Kepler value will be remains same. Now what will happen to smaller by Kepler value? Smaller by Kepler. Smaller is increasing. Kepler remains same. So smaller by Kepler value was increased now. Smaller by Kepler value was increased now. Sir, no? Okay. So because of the smaller by Kepler increment, you see in the graph, smaller by Kepler will become more than 0.368, so that electric field intensity value was increased. See the thing what I am saying. Previously on the conductor, we have some field intensity. Because of that, we got the corona. But now, after getting corona, if I check that field intensity, that is even higher than the previous number, right? That field intensity is even higher than the previous number. Then what will happen? Corona will extend, right? I don't know whether you have followed this or not. Have you understood this, what I said? Have you understood this? Yes or no? Yes. So corona gets extended like this. If the corona gets extended in this manner, what will happen? The smaller value further increase. And smaller by Kepler further increase. And E smaller value further increase. Then again the corona will be extended such that this corona may extend it towards the sheath. Cable is going to be completely damaged. All of you getting this? Right. So now tell me, is it preferable to go with the design of the cable with this dimension? Is it preferable to design the cable with this most economical size? Can we design the cable? No, we should not. We should not design the cable. For example, look all of you. If I selected smaller by Kepler value more than 0.368. More than 0.368 means I selected 0.6. Look all of you. Stop writing. I have selected 0.6. With respect to that 0.6, I have taken up this E smaller value. I have taken up that E smaller value with respect to 0.6. Okay. After taking that E smaller value, calculating that number, multiply with some factor. We get based on that we selected the dielectric material. We designed the cable. Listen all of you. With 0.6 smaller by Kepler, we designed the cable. Now, unfortunately, corona. Unfortunately, corona occurred. Corona occurred in the sense small r value will increase. Small r by capital R will increase. It will go beyond 0.6. It will go beyond 0.6. If it's going beyond 0.6, definitely field intensity further increases. Field intensity further increases. See, previously we have some field intensity, we got corona. But at present, we have higher field intensity compared to previous number. Corona will extend. Definitely cable will be damaged. Now tell me, is it preferable to design the cable for small r by capital R more than 0.368? Is it preferable to design the cable for small r by capital R more than 0.368? Yes or no? No, it is not preferable to design it. It's not preferable to design. But if you go for small r by capital R less than 0.368, less than 0.368, let's say I have selected 0.2. Selected 0.2. With respect to 0.2, I designed the cable. I designed the cable such that this is a field intensity. Based on this field intensity, I selected the material. All of you understand? Listen here, listen. This is a field intensity with respect to 0.2. Taken up the field intensity, multiplied with safety factor, selected the material strength, dielectric strength of material we selected, constructed the cable also. Constructed the cable also. Now, if corona occurs, smaller increasing, smaller is increasing. What will happen to smaller by capital R? Increases. Smaller by capital R will increase. So it will come more than 0.2. With respect to this increment, what is happening to field intensity value now? What is happening to field intensity? Increasing or decreasing? Increasing or decreasing? Field intensity is decreasing. Whenever the field intensity is decreasing, with respect to previous field intensity, you got the corona, but present field intensity is lower than the previous number. Corona may not happen. May not happen, or may not extend. See, compared to the previous dimension, the present dimension is better, right? Compared to the previous dimension, the present dimension, what you have selected is better. So in that view, always, we should, always we should select or we should design the cable on the basis of small r by capital R value less than 0.368. Less than 0.368. Can I write those statements now? Can I write those statements? All of you understood this view? So I'm writing it. So case 1. Cable designed for a dimension small r by capital R greater than or equals to 0.368. Greater than or equals to 0.368. Both I'm writing. Both unstable cases at one place. If corona occurs, what will happen? Smaller increases. Smaller by capital R increases. E smaller is increasing. Corona may extend. Cable may be damaged. Next case. Case 2. Yeah, case 2. Cable designed for smaller by capital R less than 0.368. Less than 0.368. If corona occurs, smaller increasing. Smaller by capital R increasing. But electric field intensity decreases. Corona may not extend. A cable will be safe from damages. So with respect to this, yeah, please write Please complete it. Please complete it. So in the graph, I will be showing that this is a stable operating region and this is an unstable operating region. Stable operating region. On the other side, we have the unstable operating region. So for this stability reason, always cable must be designed for small r by capital R less than 0.68, or you can say radius of the pore must be less than most economical radius. Radius of the pore must be less than the most economical radius. Obviously, it is voltage. It will be voltage. It will be deciding. Okay. Yeah. Next, let's take up the capacitance of single core cable. Capacitance of single core cable. Next slide, I am taking the capacitance. Single core, single phase cable. I'll write. Because it's single phase supply only, what we are using now. Single core, single phase. Capacitance of single core, single phase cable. Yeah, one more thing I want to tell you. This cable is going to be called generally as coaxial cable, or you can say concentric cable. This cable, what we are discussing now, is going to be called as coaxial or concentric cable. Concentric cable. Coaxial or concentric cable. Let me copy that cable diagram once. I have shown it someplace now. So this is that cable. This is a coaxial cable. Coaxial or concentric means center of the core and center of the cable is same. Center of the core and center of the cable is same. Okay. Yeah. Look, please. Look, please. This conductor is having a charge Q, voltage V. Conductor is having a charge Q, voltage V. Voltage V. Next, please listen. See, we have some capacitance formation between the core and sheath. We have a capacitance formation between core and sheath. It is that capacitance C. Generally, we write that C as Q by V. Capacitance C equals to Q by V. Right? Ground potential is 0 in it. Ground potential is 0. Q by V. Do you have any relationship between the Q and V? Do you have any relationship between the Q and V? Yes, already we discussed more. Why term may not is there? Why not definitely? Yeah, Salman Khan. Yeah, all of you listen. Saying corona may not extend, I have written no. Corona may not extend, I have written. I am not saying it is definitely. Because it's a very severe switching surge. The switching surge, what you have, it's a very severe one, causing a large field intensity on the conductor surface, causing corona. Second field intensity, what you are getting is lower than the previous number. That may be higher than the dielectric strength, right? A switching surge occurred, causing a severe corona. severe field intensity and corona. And the next second field intensity, what you are getting on the surface of corona, it may not be lower than the dielectric strength, it may be higher than that also. That corona may extend, right? So in that view, I am saying it is not, may not extend. Getting this Salman Khan? Yeah. So what is the relationship between Q and V? We have derived at some point this one. Q is equals to 2 pi epsilon into voltage by ln of capital R by small r. Okay. So let me copy it. Expression. From this expression only, you can write that capacitance equation Q equals to 2 pi epsilon into voltage by ln of capital R by small r. And you write that capacitance formula from this. Capacitance formula from this one. C is equal to 2 pi epsilon. This epsilon is like epsilon naught into epsilon r. That epsilon is equals to epsilon naught into epsilon r. So you can get Q by V. So 2 pi epsilon naught epsilon r by natural logarithm capital R by small r. 2 pi epsilon naught epsilon r by natural logarithm capital R by small r. Okay. Units will be obviously farad per meter. Units will be farad per meter because epsilon naught is 8.854 into 10 power minus 12 farad by meter. Next term. Charging current is IC. Charging current carried by the cable. Charging current carried by the cable. Charging current carried by the cable. Charging current carried by the cable is V by XC. Voltage V applied here and reactance of this capacity is XC. Reactance of this capacity is XC. So V by XC. So it will come like V into 2 pi F into capacitance. V into similar to overhead line. V into 2 pi F into capacitance we can see. Okay, yeah, done. V is operating voltage. Applied voltage to the conductor. Now, let us do one problem on this calculations what we have done till now. One problem we will do on these calculations what we have done. Check this. Take this question. A single phase concentric cable of 5 kilometer length. V in the capacitance. What's V in the capacitance? I don't know. Look here. A single phase concentric cable 5 kilometer long has capacitance of 0.2 microfarad per kilometer. The relative permittivity of the insulating material is 3.5. Epsilon R 3.5. The diameter of the inner conductor is 1.5. It is centimeters. That's missing here. 1.5 centimeters. The cable is operated at 66 kV, 50 Hz. 66 kV, 50 Hz. Okay. Calculate the inner diameter of the outer conductor. What's the meaning of this? Inner diameter of outer conductor means don't confuse. You have to find out the outer conductor radius. So outer conductor diameter. That's it. Sheath diameter we have to calculate. Sheath diameter capital D. That is 2 times of capital R. 2 times of capital R. That's it. Second one. Find RMS voltage gradient on the surface of inner conductor. Next, find the RMS value of the charging. Simple. Let's write the data. What they have done. We have a single phase cable. This point you have to highlight. Length of cable 5 kilometers. Relative permittivity of the insulating material 3.5. Capacitance 0.2 microfarad by kilometers. Capacitance is 0.2 microfarad by kilometers. Diameter of inner conductor is core diameter, small d, 1.5 centimeters. Then what is the radius of core? Pi to 0.75. 0.75 centimeters. Okay, next. Cable is operated at 66 kV, 50 Hz. Operating voltage 66 kV. Is it RMS value or peak value? Generally, operating voltage or rated voltage, whatever they give in the data, whether this value is RMS or peak, it will be RMS only. And definitely it will be RMS. Is it line to line or per phase? Is it line to line or per phase? What's the meaning of line to line? What's the meaning of line to line? We are discussing about single phase cable. Discussing about single phase cable, na? Single phase cable we are discussing, right? Single phase cable means whatever the conductor we have, that itself is going to operate. Whatever the conductor we have, that conductor itself is operating at 66 kV. It's a conductor voltage. Conductor voltage, you can write. Conductor voltage. Now, next. Inner diameter of outer conductor we have to calculate, means we have to calculate the value of capital D. That's the first term. Capital D term we have to calculate. A. So capital D is nothing but 2 into capital R value. Capital D is nothing but 2 into capital R. How to calculate that capital R? How to calculate capital R? Anybody please tell me? How to calculate that capital R? Use a capacitance. Already number you have. Use the equation. Already smaller also you know. Now you can get the capital R. So as you know, capacitance expression is 2 pi epsilon naught epsilon R by natural logarithm of capital R by small r. 2 pi epsilon naught epsilon R by natural logarithm capital R by small r. That's a capacitance. It's in farad by meter. Farad by meter. So we should keep the C also in farad by meter now. We should keep the C also in farad by meter. Just check. 0.22 micro. 10 power minus 6. 1 by kilo, 10 power minus 3. 1 by kilo, 10 power minus 3. It's in farad by meter. 0.2 into 10 power minus 6 into 10 power minus 3 farad by meter. We'll substitute that. Let's modify because we need to get capital R now. So, ln capital R by small r is equal to 2 by epsilon naught epsilon R by capacitance. Substitute the numbers. Epsilon naught 8.854 into 10 power minus 12. Epsilon R 3.5. Epsilon R is 3.5 by capacitance number 0.2 into 10 power minus 9. 0.2 into 10 power minus 9. This is a value of ln of capital R by small r. Anybody please tell me this number? How much? How much is this number? Anybody? ln of capital R by small r number. Calculate it and tell me quickly. It's not 1. It's not 1. 0.973. Okay, good. 0.973. So the value capital R by small r will come to be e power 0.973 and capital R value will be equals to small r 0.75 multiplied with e power 0.97. Tell me this capital R number. Tell me that capital R number. How many centimeters? Capital R number, how many centimeters? 1.98 centimeters. 1.98 centimeters is a capital R value. Capital R. Then if you go with capital D, 1.985. Okay, capital D value. So it is 2 into 1.985. 1.985. So it will be 3.96 or 97. We'll get it as 3.97 centimeters. 3.97 centimeters is a capital D number. Capital D number is 3.97 centimeters. Centimeters. Okay, done. Next, because 0.75 is in centimeters, right? Second one, find the RMS voltage gradient at the surface of the inner conductor. Means on the core surface, you should take up the electric field intensity. On the core surface, if you take up the electric field intensity is smaller, formula is V by smaller into ln of capital R by smaller, V by smaller into ln of capital R by smaller. So he is asking RMS voltage gradient, na? Asking the RMS voltage gradient. So we should keep the V value RMS. We should keep the voltage value RMS. Now, so you keep that operating voltage of conductor 66 kilovolts RMS by smaller 0.75 natural logarithm capital R 1.985 by 0.75. At numerator it's in kilo, denominator centimeters. So it's kV by centimeter. 66 operating voltage, 0.75 smaller, ln of capital R by smaller, 1.985 by 0.7. It will be coming in kilovolts per centimeter. How much is this? Anybody tell me please? This number 90.41 kV per centimeter. On the surface of core, electric field intensity you get like 90.41 kV per centimeter RMS. That's B. Next, what's the part C given? Find RMS value of charging current. So even though he didn't mention about RMS charging current calculation, I'm saying charging current, we have to calculate RMS value of charging current even though he didn't mention it, RMS. What is charging current formula? V into 2 pi f into capacitance. V into 2 pi f into capacitance is the charging current formula. What is voltage? 66 kilo, you know already. By 50 frequency. Capacitance how much? 0.2 into 10 power minus 6 into 10 power minus 3 farad by meter. 0.2 into 10 power minus 9 farad per meter. See, the overall units of this current will be amperes per meter because capacitance you kept in per meter. Capacitance you are keeping in per meter. So overall units will be ampere per meter. Electric field intensity or no, electric field intensity, potential gradient, both are same. Electric field intensity, potential gradient, both are same. It's not voltage. Yeah, how much is this? 4.146. Are you getting the other number? 146 milliampere per meter. Milli means 10 power minus 3. 10 power minus 3 ampere per meter. What's the length of cable given in the data? 5 kilometers. That you multiply to this, we get the total charging current. So total charging current will be equal to 4.146 into 10 power minus 3 ampere per meter into 5 into 10 power 3 kilometers. How much is this? I think around 20.7. 20.7 amperes. Total charging current value 20.7 amperes. Only for 5 kilometers. Only for 5 kilometers, charging current is coming 20. Very large. Yes or no? This is one of the major difficulty with the cable. Because of this charging current only, heating production in the cable is also very, very high. Heat production in the cable is also very, very high. Yeah. Next thing. Let's think about the three-phase supply. three-phase supply by using cables. Okay, three-phase power transmission by using cables. Three-phase power transmission by using cables. Three-phase power transmission by underground cables. Actually, this three-phase power transmission can be done by two ways. Three-phase power transmission, it can be done by two ways. One, using one three-core cable, only one three-core cable. Second one, using three single-core cables separately. Single-core cable separate, phase A cable separate, phase B separate, phase C separate. Number one, I say case one is using one three-core cable. Using one three-core cable. Three-core cable. Okay, let me show it. So it's a outer conductor, so-called sheath, and it's a conductor A. I can say core one. Core one. So it's a conductor one, a core one, you can say. I'm showing core two. That core two. I will show core three lines. These are the three conductors. Core one corresponding to phase A, I write, and it's a core two corresponding to phase B, and there's a core three corresponding to phase C. And sheath connected to ground. Sheath connected to ground, and this is that insulation. This is the insulation. Next, case two, I'll call here case two. Case two. Using three single core cables. Using three one core cables. One core cables. Okay. Yeah, see this. This is the single core cable. I'm going to show one single core. Right. So like this, you can have one single core cable, right? So like that, we have three cables repeated. So cable corresponding to phase A, phase B, and then cable corresponding to phase. Cable corresponding to phase. So each sheath is connected to ground, connected to ground. And this is A, B, C. A, B, C conductors or cables, A, B, C cables. Using three single core cables, one technique, other technique we are saying using one three core cable. Yeah, next. See, in this case, you don't get any mutual interaction from one conductor to other conductor at all, because each and every one is separate system. Because each and every one is separately grounded. No, each sheath is separately grounded, so you don't get any interaction from one cable to other cable. So in this case, capacitance per phase is very easy to write. That is nothing but capacitance per phase of any one of the things. First of all, before moving to that, first tell me, in which one? Is it three core cable or single core cables? Which one? Heat production will be less. heat production will be less. Which one? Is it 3 single core cables or 1 3 core cable? Case 2. Definitely in case 2, the heat production is less. So it will be used for voltage levels higher than 33 kV. Okay. So it is used for voltages higher than 33 kVs. Whereas this one, heat production is a bit more because area provided for heat dissipation is less. The area for heat dissipation is less. And this is used for voltage levels less than or equals to 33 kV. Some places we can see 33 kV 3 core cables also. 33 kV 3 core cables also you will see. And some places for more than 33 kV you will be using for single core cables. Next, capacitance calculation we have to concentrate mainly as I said. Capacitance per phase in the first case is nothing but capacitance of any one of the single core cable. Capacitance of any one of the single core cable. It will be like 2 pi epsilon naught epsilon r by natural logarithm capital R by small r in farad by meter. Capacitance per phase in case of 3 single core cables is this one. But for this, we should know how to get the capacitance per phase. 3 core cable is our concentration. 3 core 3 phase cable. 3 core 3 phase cable. Capacitance per phase calculation we want to concentrate further. Okay. Right. So let's take in the next heading. Next heading. 3 core C per phase calculation. Calculation for 3 core 3 phase underground cable. 3 core 3 phase underground cable. Capacitance per phase calculation for 3 core 3 phase underground cable. Okay? Yeah. Next. Let us think about this diagram. First, let's think about this diagram. This cable, what we have shown here, it's a type of symmetrical cable. Kindly observe my words. Kindly observe my words. It's a type of symmetrical cable. Symmetrical cable in the sense, distance from A to sheet, distance from B to sheet, distance from C to sheet, these three are equal. These three are equal. Let's say it's D1. Some number D1. Similarly, distance from A to B, distance from B to C, distance from C to A, these three also equal. It is D2. Distance from A to B, B to C, C to A, these three also equal. That is D2. Outer distances D1, D1, D1. Okay, right. This is the meaning of symmetrical cable. Symmetrical cable. Sometimes you can call this as belted cable. Belted cable. Belted cable. Belted cable. Yeah, for that one we are concentrating now. Sir, will the core in the 3 core cable are stranded one? This is also stranded. ABC are stranded conductors. Let's take up that cable now. Let's take up that cable, what we said now. So it's a 3 core cable. Outer conductor, sheet, you can say. Now I will show 3 conductors here. A, B, C, 3 conductors. Small size I am showing. Show that here. This is a conductor A, phase A. I can show it is a phase B. And phase C I am showing now. Like this. So these are ABC conductors operating at certain voltages like B phase at an angle 0, B phase at an angle minus 120, B phase at an angle plus 120. B phase at an angle 0, B phase at an angle minus 120, B phase at an angle plus 120. Yeah, look here please. Okay. See, the sheet is connected to ground already we have mentioned. Sheet is connected to ground, maybe operating at 0 potential. Now just check the conditions for the capacitance formation desired. Conditions for the capacitance formation, right? P phase at an angle 0 degree, B phase at an angle -120. This is B phase at an angle plus. Two conducting bodies should have. Between that, we should have some dielectric material. Two conducting bodies, and we should have a dielectric material, and there should be potential gap. There should be some potential gap. Okay. So for that, A2 sheath is operating at 0, na? A2 sheath, definitely a capacitance gets formed. B2 sheath also we get some capacitance formation. C2 sheath also we get some capacitance formation. A2 sheath, B2 sheath, C2 sheath. How will be these three capacitances? Equal or unequal? Anybody? How will be these three capacitances? Equal or unequal? Equal. Why? Why in the sense distances are equal, D1. Distances are equal, not voltage. Distances are equal. So this is CS we call capacitance from any one core to sheath. Capacitance from any one core to sheath. Any one core to sheath. Next, definitely there exists a capacitance between A and B, B and C, C and E. So I can say A to B, we have CC, B to C, again we have a capacitance of CC, C to A, we have a capacitance of CC. So that CC is the capacitance between any two conductors. Capacitance between any two conductors or any two cores. Capacitance between any two conductors, else you can say capacitance between any two cores. These three also equal. Next, listen all of you, listen. Capacitance per phase. Capacitance per phase means effective capacitance from any one of the phase conductor to neutral. Capacitance per phase means effective capacitance from any one of the phase conductor to neutral. So this whole distribution diagram we should modify. First you tell me this. How will be these CCs are connected? How the three CCs are connected? Delta. Three CCs are connected in delta. Next, listen, delta. This delta we convert to star so that we get some neutral point here in the star. We get a neutral point. That neutral point voltage will be 0. Neutral point voltage will be 0. That point and sheath you can join together because both are having equal potential, and then we will simplify it. Okay, so first what you will write? Convert delta connected CCs into star. Convert delta connected CCs into star. Okay, see this diagram, cable diagram. Already we have that conductor to sheath capacitances like CS. Conductor to sheath capacitances we have like CS. And this is sheath already grounded, we said. Now this delta we are converting into star. This is the conversion we are making now. Okay, and this point is called as neutral. Point is called as neutral. What will be each capacitance here? In this star, what will be that each capacitance value? 3 cc. 3 cc it will come. Okay, by doing that delta to star conversion, each capacitance will come to be 3 cc. 3 cc. And this neutral point, what we have now in this star and the sheath, these two will be shorted because you know this neutral point is operating at 0 potential, sheath is also operating at 0 potential. These two can be shorted. This we can call as virtual short circuit. Called as virtual short circuit. That will be called as virtual short circuit. Virtual short circuit, it's nothing but 2 points having same potential, we can join them together in the circuit. two points are having same potential means you can join them, even though there is no physical contact. Even though there is no physical contact, electrically you can connect. Electrically you can connect. Okay, now you please tell me. Please. How these 3cc and CS are connected? How the 3cc and CS are connected? Tell me please. Parallel? Parallel. Okay. This 3cc CS parallel. These two also in parallel. Now let me write. Let me show the modified diagram. Modified diagram. So CS and 3cc in parallel, like this you can see. CS and 3cc will be in parallel. And here also. CS and 3cc in parallel. And here also. CS and 3cc in parallel. And this is a sheet which is connected to ground. And you know, each conductor is operating at a voltage V phase, but we have a potential gap. Now tell me, what is the effective capacitance from phase A to neutral or phase A to sheet? Effective capacitance from phase A to sheet. That is parallel combination of these two will come to be CS plus 3cc. That is called as per phase capacitance of the cable. Effective capacitance from any one phase to neutral, or simply we can say capacitance per phase, C per phase equal to parallel combination of CS and 3cc. Parallel combination of CS and 3cc. So it will come to be CS plus 3cc. That's the capacitance per phase. That's the capacitance per phase. Yeah. So I think all of you getting it. Now, what is the charging current per phase? Charging current per phase is nothing but V phase by XC per phase. Simple formula, same as overhead line. Same as overhead line. Charging current per phase. Charging current per phase be IC per phase equal to phase voltage by XC per phase. You can write. So you can say V phase into 2 pi f C per phase. V phase into 2 pi f C per phase. That is a charging current per phase. Charging current per phase. Next. What is the amount of reactive power delivered by the cable per phase? Q delivered by the cable per phase. Delivered by cable per phase. Sometimes you can call this one as charging wires. Okay. Per phase, or you can say simply charging wires. Charging wires. So it is QC per phase, you can write. QC per phase. What's the formula for QC per phase? Phase voltage square by XC per phase. Phase voltage square by XC per phase. And if you write the QC 3 phase, it will be 3 into phase voltage square by XC per phase. 3 into phase voltage square by XC per phase. Like this you can see. Charging wires. Yeah, okay. Fine. In tomorrow class, we will be discussing about calculation of the CS and CC. Calculation of the CS and CC will discuss some experiments we are going to conduct to find out these things. After that, we will move on to what we call losses in the cables, right? And last topic will be insulators, and little we discuss about the distribution system. Right? Tomorrow and day after tomorrow. Means by 9th, we will be finishing the syllabus. Right? So please wait for 5 minutes. Please wait for 5 minutes. I will resume and I will answer your doubts. Only 5 minutes. I will come back within 5 minutes. If you have any doubts, you can stay. You can stay here and we'll discuss. So I came back. Please kindly tell me what's the doubts you have. Please raise your hands. I will make all the hands low. Please kindly raise your hands. Imtiaz. Tell me, Imtiaz.
Good morning, sir.
Come on.
Sir, in the
Is my voice is okay, Imtiaz?
yes, sir. It's okay, sir.
During the class.
Yes, sir. Okay, sir.
Little echo. That's it.
No, sir.
Okay. Tell me. What's your doubt?
Sir, for the electric field intensity on the core will be maximum, no, sir.
Yeah.
Where we are taking V is equal to 0.368 to R, no, sir. That is the maximum value.
What's the maximum value?
Okay.
Okay. That is maximum field intensity experienced by the dielectric material for the dimension.
For the dimension. Sir, it's confusing between that we are taking the maximum here.
See, with this condition of small r by capital R equals to 0.368, you got the field intensity as this number.
Yes, sir.
It is heading. So this is at small r by capital R equals to E.
Yes, sir.
Okay. Now tell me, what's your doubt here?
Sir, we are taking here is the maximum. No, sir. At the core surface.
Okay. Yes.
But we are taking in the curve is the minimum is equal to core surface in that.
This one. Okay. So this E minimum is E smaller, right? E smaller minimum value. This is confusing. Is it okay now?
Okay, sir.
All the curve represents E smaller only. This is the lowest value of E smaller.
I forgot the year, sir.
That is coming for this dimension of small r by capital R equals to 0.368.
Okay, sir.
Any other doubt here?
No, sir. Sir, one request, sir. Maybe day after tomorrow is our last class, no, sir.
Yes.
Could you tell about the IIC Bangalore for our motivation?
Yeah,
because
sure.
of
At the end I will tell.
Okay, sir. Sir, one more, sir. Sir, for triple we have two paper, no, sir. Instrumentation LEC, which will better for us, sir.
You go for electrical only. Oh, you want to take one more paper, right?
Yes, sir.
Instrumentation you go.
Instrumentation.
Because in the electronics communication ECE, are you able to write ECE also?
Sir, I study only electrical, sir. ECE I did not touch any topic.
So if that's the case, you go for IN, instrumentation.
Okay, sir. Sir, if possible, both are on same day, sir, morning and afternoon.
Maybe possible. Maybe.
Which will have 1 week gap, sir. I mean, because of the last since for 2-3 years.
It's happened in last time, but it may not be for future. We don't know.
Okay, sir.
Those people, IIT people will give that much facility for us.
1 day gap is also sufficient because
1 day gap may or may not come. We can't say it yet. Till the notification comes, we can't say it.
Okay, sir.
Okay.
Okay, sir. Thank you so much, sir.
Sir.
Tell me.
Sir, in the first part where we explained that R phase of the cable is greater than that of the
Tell me, what's your doubt?
Sir, in that my doubt is when temperature increases, you did mention that the resistance of the cable will actually increase. It is increasing, but if you increase the temperature, wouldn't this air it will expand, no, sir, the material?
Core. I'm talking about core resistance.
But even though it's a metal only, no, sir.
You are talking about thermal expansion.
Yes, sir.
Thermal expansion is length.
Oh, it will not become in along the radius.
It may not.
Okay, that's what confused me when you explained about temperature, sir.
Yeah.
And sir, another one, sir.
So again, there, Vishnu, you are comparing two things. One is thermal expansion coefficient. Next one is temperature coefficient of resistance. Dominant will come among the two.
So among the two, the one which is dominating will decide
that will cause a major change for the resistance.
Okay, sir. Okay, sir. Okay. And sir, one more thing. This you did mention that while you are designing a cable, we go for minimum core electric field.
Yeah.
PR min, and then later on you describe that we go for a value or R by R less than that of 0.368.
Yes, yes.
So, but at the same time, if you're going for a lower radius, wouldn't, like when you're designing a cable, you consider both voltage as well as the current rating, no, sir?
Okay, that is okay, but we are fixing our voltage rating. The current rating will change now.
Yes, sir.
We are fixing the voltage. 1 minute, 1 minute. I'll come.
Okay, so the priority is for the priority we go for is fixing the minimizing this electric field intensity, sir. Then, hello.
Yes, sorry, Imtiaz. Vishnu, tell me, Vishnu, please.
Sir, same thing, sir.
See,
When you're designing,
listen. Voltage rating we are fixing, no? We are assuming voltage is constant, remains same.
yes, sir.
And current rating will change, definitely. If you are changing radius of conductor, current rating will change, power rating will change. We are not saying this for constant power rating, right?
Okay, sir.
Okay.
And sir, and regarding this only, sir, this corona may reduce this because maybe you can't completely take this corona out, even if
yes.
ER reduces.
So I said, no, if there is a strong surge occurred, even though you are following this condition, cable may damage. Even though you follow the second case only for design, still the cable may damage. Chances are there.
Okay. And sir,
that's why I said corona may not extend.
And sir, and this cables are used for anything greater than 33 kV or what, sir?
See, I have seen a cable, 130 kV cable also in Hyderabad. Seen a 130 kV cable for power transmission.
So then, wouldn't there be any leakage current to the ground or something? It would be more.
Always charging current will be there.
Okay.
Always charging current will be there, na?
And it will cause some same time there will be some other grounds. Telephone lines also will be underground, so interference wouldn't be more for 132 kV, sir.
Definitely, interference might be there nearby underground communication system. Definitely, there is a interference. That is one of the disadvantage of using underground cables. Definitely.
Okay, sir. So
but you have to think one more thing also, Vishnu.
Yes,
definitely, there is an interference. But 3 conductors are causing that, na? Phase A, phase B, phase C. That net interference may be less.
Okay, sir.
Because of this little cancellation.
Okay, because they are 120-degree phase shifted from each other.
Yeah. But if you are using 134 cable, that issue may not come. Because outgoing flux itself is 0, right?
Yes, sir.
Some of the 3 fluxes will come 0. Outgoing flux is 0. So we may not get that interference if we are using 3-core cable. But if you are using single-core cables, there is an issue. There is
a 3-core cable, the flux gets cancelled within the material.
Yes, within the sheath itself. Yes.
Okay, sir. And I think that's all, sir. Thank you, sir.
Yeah, fine. Naveen Sai.
Good morning, sir. My doubt is from last class, sir. I have 3 doubts. We are using spear gap for. Okay, sir.
Yeah, inductance formula will be as it is. We have discussed for the single core cable. This one.
Sir.
1 minute, please.
Oh.
Capacitance calculation we have done. There I will write the inductance also. See, for this cable, inductance will be mu naught by 2 pi ln capital R by small r. or R dash also you can take 0.77. This formula you can use for inductance. Yeah, tell me, Sai, Naveen Sai, tell me.
Sir, we are using spear gap for protection of series capacitor, no, sir?
Yes, correct.
In the faulted case, when the spear gap is short circuited.
Yes.
So there is,
And you
I
will
mean,
be having a doubt that if that is zero, capacitor voltage is also zero.
that's it, sir. I mean, if the
That
if
may
we
be
can
zero,
think,
but again, whenever that discharge happened,
sir,
whenever the spear gap got broken,
sir,
it will continue to carry the current, right? Because
yes,
of
sir.
that current flow, that arc will be sustained.
Okay, sir.
Okay, whenever the fault got removed, then the current will be automatically interrupted, then the arc will go away.
Okay, sir. I mean, we should think that it will be happen in very short time. So capacitor
Not short time,
may not.
not short time. Listen, Sai.
Sir.
Once after getting that ionization between the spheres,
Okay.
we have a large amount of heat development.
Yes, sir.
That heat development will continue the ionization,
Yes, sir.
like your circuit breaker.
Yes, sir. Yes, sir.
Initially, spark is forming between them because of high field intensity.
Yes, sir.
Then it is going to be continued because of the heat development.
Okay.
So that current will flow.
Okay, sir.
And voltage will be close to zero. So capacitor will experience a voltage close to zero. Capacity is same.
Okay, yes, sir. Yes, sir.
Whenever the fault got disconnected, came to normal condition, that arc will be disappeared. Spear gap arc will be disappeared.
Yes,
it will act as open circuit.
Yes.
And your current will
Yes,
flow
sir.
through capacitor.
Okay, sir.
Okay.
Yes, sir. And my second doubt is in synchronous condenser, while calculating Q synchronous, I mean the reactive power it delivered, we have this formula, no, sir. P into tan phi 1
Yes,
minus
correct,
tan phi 2.
correct.
Synchronous condenser means we are taking no load condition, no, sir. If we consider ideal condition, the real power should be zero here.
Ideal condition.
And
but you
yes,
don't
sir.
have ideal conditions, right, Naveen?
Okay, sir. In this case, we
Practically, you
have to
don't have
consider
ideal
the
conditions.
losses. Okay,
Then
sir.
P2, what I have written there, P2 will become P1 plus power loss.
Okay, sir.
P1 plus power loss are real power consumed by synchronous condenser.
Yes, sir. Okay, sir.
Okay.
Yes, sir. And my last doubt is the disadvantage of using synchronous motor. We have taken 4
Stability
point.
issue.
Yes, sir. Stability issue. Generally, stability will be affected when there is a change in reactance of line.
Have you attended FNS?
Yes, sir.
If you are adding synchronous motor, will it swing with the existing system or not swinging?
No, sir. It will not swing. It is.
It will not swing. Good. It will not swing. Then what's the M equivalent? Decrease, na?
Yes, sir.
Then obviously stability is less.
Okay, sir. And the fault level of the system is increasing here, sir.
That we discussed in fault analysis. Synchronous motor is supplying fault current.
Okay, sir.
Assumptions we made, some assumptions, just to go through it. That's why I have not explained again in detail.
Okay, sir. Okay, sir. That's it, sir. Thank you.
Pratyush.
Hello, sir.
Tell me, Pratyush.
Sir, yesterday I have discussed one problem regarding phase modifier, no, sir.
Yeah.
That 3 power equivalent 1000 kilowatt. Sir, in that question, if we have done this method, sir, like we have P1, P2, P3 and cos phi 1, cos phi 2, cos phi 3, and we'll calculate S, and when we equivalent S1 plus S2 plus S3, and we'll calculate cos phi then, sir.
What is the test?
Sir, S1 plus S2 plus S3. Sir.
What is that S? What is that S you are calling?
Sir, apparent power, sir.
Okay, tell me. Are you supplying apparent power or complex power?
Complex power, sir.
Complex power, you should sum up them.
Yes, sir. Sir, that only I'm my doubt, sir. Why that method is wrong, sir?
You are supplying complex power. You should not sum up complex powers, right? Sorry, apparent powers, right?
Yes, sir.
Satyush, I will tell you one very basic thing. Understood?
Yes, sir. Yes, sir.
Not understood? Look
sir,
here.
Means, yes,
listen. This is a bus. I have 3 loads connected to this one.
Yes, sir.
Okay. This is
yes,
first load is taking a current I1, 10 at an angle 0 degree amperes. Second load is taking a current of 20 at an angle minus 45 degree amperes.
Yes, sir.
Third load is taking a current 10 at an angle 45 degree amperes.
Yes, sir.
What is current supplied by source?
It is the phasor sum of
10
I1 plus I2
plus
plus.
20 plus 10. Can I write this?
No, sir.
Why?
Sir, as it is a AC, should be a phasor.
Actually, you should do for S also, right?
Okay, sir.
The complex power and it's S1, S2, S3.
Okay, sir.
See, S equals to S1 plus S2 plus S3 else. I equal to I1 plus I2 plus I3. Okay.
Yes, sir.
And I conjugate equals to I1 conjugate plus I2 conjugate plus I3 conjugate. Okay.
Okay, sir.
Multiply with V. VI1 conjugate plus VI2 conjugate plus VI3 conjugate. Okay. That's it. Complex for S equals to S1 plus S2. Yes.
Okay, sir.
Understanding?
Yes, sir. Yes, sir.
You are not summing up magnitudes, you are summing up phasors.
Yes, sir.
Same thing I have written, nothing more than that.
Okay, sir.
Okay.
Okay, sir. Sir, another one, sir. Sir, this is general doubt, sir. Sir, what is the method we use to absorb the surge in case of switching over voltage, sir?
Can you repeat again? What is the?
What is the method we use to absorb the surge, sir? Because of switching over voltage.
Surge.
Sir, lightning over voltage also same, sir. Lightning arrestor. Sir, is there any difference between lightning?
Difference in the sense, see, equipment wise, you don't have any difference.
Yes, sir.
Equipment wise, you don't have a difference, but rating may be different.
Sir, can we use the spark gap, sir, for surge?
Spark gap only. Spark gap is also one of the surge arrestor.
Okay, sir. Sir, I mean, sir, I saw one lightning arrestor in substation, sir. Sir,
they might be using some material also.
Yes, sir.
Silicon carbide or some other material they might be using. Number of spark gaps connected in series will also act as a surge arrestor.
Okay, sir.
There are different types of surge arrestors, na?
Yes, sir. Yes, sir.
All are working for the same purpose. Might be voltage rating is different. Their efficient operation may be different.
Okay, sir. Sir, in case of surge arrestors also, those high energy will be transferred to ground only, sir?
Ground, yes.
Okay, sir. Thank you, sir.
Both me.
Hello, sir.
Tell me about.
Sir, when we are using the P equals to VI cos pi and Q equals to V sin pi and P equals to VE by X sin dental, like that means I want to.
That depends upon the availability of the values both way.
Yes, sir.
It depends upon the availability. For example, if this is one line here,
Yes,
okay,
sir.
and this is some voltage V1, so it is mod V1 at an angle delta, and this is some voltage V2. You say it is mod V2 at an angle 0, and you have this current as I.
Yes,
Okay.
sir.
Now, if you want, this I also I will take. I is equals to some magnitude and associated angle something like phi, some angle.
Yes, sir.
Okay. Now, what is the real power delivered by the bus 1? P. I will have two equations for this. One is mod V1 mod I cos of delta minus phi. This is one equation.
Yes, sir.
Because delta minus phi is an angle gap between voltage and currents, right?
Yes, sir. Yes.
Same equation you can write in terms of these voltages in the two bus system. Mod V1 mod V2 by X into sine of delta minus 0, it will be sine delta.
Yes, sir.
Both will give same number.
Yes, sir.
Okay. Then you have to use VI into cosine of angle between voltage and current. If you know voltage and current values.
Yes, sir.
Or else if you know power factor.
Yes,
Right?
sir.
Yes or no? When
Yes,
we
sir.
have to use this V1, V2 by X into sine delta, if you know voltage magnitudes and the angle difference.
Yes, sir. Okay. That's the only
See,
difference.
actually, listen, both me.
Yes, sir.
For example, I know these voltages and you know this impedance.
Yes, sir.
I can calculate it V1, V2 by X into sine delta, you get some number. Actually, this equation was derived from the first one only.
Yes, sir.
This equation, second equation was derived from the first one. What is correct I? We have to calculate V1 minus V2 by Jx. You take magnitude of that current, substitute here,
Yes, sir.
and you simplify this. Finally, you get this equation.
Yes, sir.
Both are equivalent to each other.
Yes, sir. In synchronous motor also means in motor,
yeah.
any motor.
Anyway, actually, you say we have two equations for real power. One is Vi cos phi. Other
Mm.
equation is V1, V2 by X into sine delta. According to the requirement in the problem, you have to apply any one of the equations. Both equations will give same number, same value.
Okay,
Okay.
sir. Okay, okay. Well, sir. Thank you, sir.
Shiva,
Hello, sir. Good morning, sir.
tell me. Good morning, Shiva.
Sir, 13F, sir.
Okay.
Sir, while calculating the first expression R insulation, why you took dx instead of L?
What is it? Can you tell me again?
No, sir. The first expression, that the rho insulation divided by 2 pi x into L into dx.
This one.
So why you took dx?
Because I have to find the starting from surface of the core to sheath, right?
Okay, sir.
Actually, two things you have to cover, Shiva. One is total length of cable.
Yes, sir.
Next one is from small r to capital R.
Yes, sir.
Already in this formula, we have covered total length of cable.
Okay.
Now we should cover from small r to capital R.
Okay, for that small dx, we considered like dr.
But this is a resistance for small dx only. The dx you should expand from small r to capital R, right?
Okay, okay, sir. So is it, so is the dx is the perpendicular distance, right, sir?
Yes, correct.
Okay, sir. Sir, and then at 38, sorry, 38F, sir.
30?
38.
Okay.
Sir, I don't get how that CS and 3CC are in parallel, sir.
That is delta to start. Parallel. Okay.
Yes.
A2 neutral 3cc.
Okay, sir.
Neutral and sheath are same.
Yes, sir.
A2 sheath CS.
Okay, sir.
Then obviously these two in parallel, right?
Yes, sir. Yes, I got it.
You drag neutral onto sheath, you will get it.
Okay.
Okay.
So, and then that most economical size of cable.
Tell me.
So we calculated R is equal to 0.368 times R. So is that the physical radius that will present in cable, sir?
So we have, if you design that in that manner, you will get the most economical.
But anyway, we are going for like minimum insulation only, no, sir.
Now, first, not minimum insulation. First, we have done how to reduce the cost of cable that we have discussed.
Okay, sir.
Okay, later on, what I said, even though you say by taking this radius, you are getting most economical value, but still it is not suggestible because of this phenomenon.
Okay, sir. Okay, sir.
That's the thing we are commenting. So ultimate conclusion is you should not go for most economical radius of the cable. If you do that, your cable is going to be damaged.
Yeah. Okay, sir.
Okay.
Yes. Okay, sir. That's it, sir.
Yeah.
Thank you, sir.
Manivan.
Hello, sir. If we use the cable for a practical inductive load, will it improve power factor?
Which power factor?
Power factor of the load, because
load
in last page we
listen. Power factor of load, who will decide? Load will decide.
Because in the transmission line, the capacitor, virtual capacitor, actually provide a reactive power.
I understood your doubt. Please tell me. You connected. You are saying that, sir, we have a lagging load, sir. If you connect a cable, the power factor will improve it or not. That's your doubt, right?
Yes.
Sir, which power factor will improve? Load will not change. Your source power factor will improve.
Does it actually act as a shunt capacitor?
That's it. It's a shunt capacitor only.
artificially we are providing. Instead of that, it's actually naturally
Naturally it's
simulated
coming from cable. Naturally it's
simulated,
coming from
okay.
cable. Yeah.
Sir, in the charge current, once the virtual capacitor gets charged, it won't take any extra current once it charges to supply
AC
voltage,
supply,
right?
AC supply, Manivandan AC supply.
Okay.
Continuous charging, discharging, no?
Yes. Then another point of view, the voltage drop across the capacitor will be for a long transmission. It will be more, na? It won't be used for a long distance in case of AC, right?
A cable you are talking.
Cable. For
We'll
AC,
discuss length variation in the cable later. We don't use it for longer lengths. Why it is so? Is high charging current is one reason.
That's it.
Shraddha,
Yes, sir.
tell me, Shraddha.
Sir, how heat produced will be more for 3-core cable?
Area. How much area you are providing for dissipation? Very small area, right?
Yes, sir.
You are providing a small area for heat dissipation.
Okay.
This one only. But here each cable having their own area, separate areas.
Yes, sir.
Then dissipation will be proper in single core cables as compared to 1 3-core cable. Okay.
Yes, sir. And sir, what is the purpose of serving in UG cable?
To avoid the corrosion of the armoring.
Okay. So will it not get corroded, the outermost layer?
Which one? Serving.
Outermost serving, huh? Yes, sir.
Anyhow, we kept many layers between that, right? Even though that serving is getting damaged little bit.
Okay.
But still it may not touch the conductor and shear, what you call that, insulation, right?
Yes. And sir, why we calculated insulation resistance for HVDC? Why not for AC?
AC also will get same number.
Okay.
Why I have shown DC means show that circuit.
Okay, sir.
To tell you simply insulation resistance is in parallel for that purpose.
So cable will have resistance and capacitance only. Inductance value will be 0.
Series inductance will be there, na?
Yeah. Yes.
Series RL, shunt CG, as it is as a overhead line. For any conductor, not only overhead line or any even this wire also, will have series RL, shunt CG.
Yes, sir.
Okay.
Yeah. So that insulation resistance is G value.
You can take it. Yes, G value.
And sir, can you once again?
And we have one more thing. We have something called as dielectric loss and all.
Okay.
That also we should involve in that. Our insulation is not only one thing. There are some other factors which will come in shunt.
Okay.
Our insulation is a body resistance. Insulation body resistance.
Okay, sir.
There is one loss called as dielectric loss.
Yes, sir.
Which we discuss tomorrow.
Okay.
That
sir.
also we should keep as a shunt element only.
Okay, sir.
By taking up all the things, you should keep that G.
Yes, sir.
Yeah. Tell me.
And sir, can you once again explain proximity effect?
See, two conductors one beside the other. Because of conductor 1 flux, magnetic flux, causing an EMF in the second conductor.
Okay.
That is creating some eddy currents.
Right.
These eddy currents will be disturbing the current distribution in the second conductor.
Yes, sir.
So then definitely the area through which current passing may be less.
Okay.
Then obviously if the area of cross section through which current flow is less, resistance will be more, na?
Yes, sir.
That's what we are saying proximity effect. Because of proximity effect, there is a chance of having more resistance for the conductor.
Okay. So do we consider this in overhead lines?
Because distance is more in overhead lines, conductor to conductor gap.
Okay, so it will be negligible.
Negligible. But in cables, we have to consider.
Okay, sir. Thank you, sir.
Yeah. So any more doubts, please raise your hands. Else we'll close the session. Sri.
Morning, sir.
Tell me, Sri.
Sir, in the that fault in the power system, when that motor will be provide power to that synchronous motor will provide power means release its energy.
Releasing its energy. Yes.
Energy. Then if I go for the phasor diagram, that current direction is in opposite to that previous one.
Okay.
Then can I say that the energy stored in the magnetic field is getting discharged?
Not magnetic field. Mechanical energy is getting discharged.
But it is behaving as a generator then.
Acting as generator, you can say, but it's not supplying. Okay, you can treat it as a generator, no issue. Yes, you can treat it.
Generator means that motor is converted to now generator, no?
Yes. But it's not. It may not supply any real power. Supplying only reactive.
Reactive power only.
Yeah, I'll say it's a voltage source. Black as a voltage source.
Okay. Yes. And sir, in a VSC, that is voltage source converter. Sir, in the Fourier series expansion, we are getting some sin 5 term in the input power factor actually, destruction factor. Sorry, displacement factor.
See, actually, it will be introducing harmonics. That's the one of the disadvantage of using StatCom.
Yes, but in that is, if all elements are ideal, there is no source inductance, then we can get that the power in the output is only that is the real power.
You are not using it for real power, right?
But in the input side, there is some reactive power. Reactive power is going and then coming back. Means it will be overall it will be 0. But in that case, if we will from Fourier series we are calculating, there is some reactive power. That is reactive power. Which element is going to take?
What's your doubt in that side? What's your doubt exactly? Tell me.
Exactly means that reactive power there is, because in the load side, if a continuous conduction, there is inductor is present.
Okay.
But that input reactive power, which element is responsible for that input reactive power supplied by the source in the converter actually means in the
you are showing one DC voltage source at the end.
Yes,
charged capacity you are keeping. Charged capacity you are keeping. There is some energy stored in that. Because of that voltage, what you are having there, you are converting that to AC.
Yes.
Okay. And you are maintaining a gap, potential gap between the converter output voltage and system voltage.
Yes.
Because of that voltage gap, there is a reactive power circulation.
But that reactive power circulation is due to that capacitive element.
Capacitive element.
But in designing,
I don't say it's capacitive. It's a battery you are keeping on one side of converter, voltage source converter. Other side you are getting AC supply, just like an inverter action.
Yes.
But we are not supplying any real power.
Okay.
So battery will maintain the voltage as it is.
Yes.
Okay, up to certain amount of time. But generally there is a loss, minor amount of loss. Because of that charge is getting down.
But that reactive element is coming from only the capacitor.
Capacitor, you can not capacitor exactly. You don't say that as a capacitor. You say it as simply AC voltage, what it is produced on AC side of voltage source converter.
Okay. Okay. That transmission line will be take some reactive power. And, that reactive power is somehow.
You talk in the manner of energy, right? Talk in the manner of energy. In one cycle, this converter is supplying energy to line, and in the other cycle, it's taking back.
Taking back, yes.
Energy, talk in energy.
Yes, yes, yes.
Then there is no loss of energy for the converter.
Okay. There is
but
no loss.
There is an element loss, right? Like switching losses, you say, or body losses.
But
There are
for
some
that,
differences.
but in some diagram, we can say that this is for that capacitor, the voltage is nearly constant. Means there is no fluctuations.
Yes, nearly constant. Yes.
Constant. Then we can say that reactive power will completely going to be zero.
You are converting that to AC, right? DC you are converting to AC, na first.
DC converting to AC, yes.
Then you are talking about reactive power and all, na?
Okay. Actually, I have doubt that from where that reactive power actually came.
Okay. Have you understood synchronous motor clearly?
Yes, sir. Synchronous.
Synchronous motor.
Yes.
If it is a synchronous motor and it's a rotor body, I am showing field winding and all will be there. And we have a DC source here.
Yes.
Okay. And this is three-phase supply coming or whatever it is. Operating under no load.
No load. Yes.
It is a bus bar. Motor it is.
Yes.
You say it's a over excitation condition. Is it supplying reactive power into the bus?
Yes.
How it is supplying?
Okay, that energy stored in the magnetic pump.
This is nothing but DC to AC conversion, right?
DC to AC conversion.
This is DC source you are applying. And you are creating one AC source, right?
Yes.
It will act as a AC source simply. As a whole, it will act as a AC source only, na?
Okay. Yes, AC source. Okay.
Rather than mechanical conversion, you are doing electrical conversion by means of converter. It's also a converter, mechanical converter.
Yes. And see, after
But
that
one thing, you have to rotate the rotor by some means. Maybe by drawing real power from grid or by some other way, whatever it is, you have to rotate the rotor.
Yes.
Okay. But there you have to operate the switches.
Yes. Okay. Means after load connected, then we can say that is reactive power is taking or not. Means
Whether
that is
the load is there or load is not there, current will flow.
Current will be flow.
Current will exist, because of voltage difference.
Yes.
Then definitely there is a current flow means we don't have real power flow, so definitely there is reactive power.
Okay. Means that current will reactive power. Sir,
one more thing, Swain. If you don't have real power exchange, that does mean that current equals zero.
Yes.
If you don't have real power exchange, it's not a meaning to say current equals zero. Who will decide current? Voltage difference will decide the current.
Voltage.
That's it. Okay.
Sir, more deep about that concept.
Which concept you want?
Sir?
Which concept?
That in the synchronous motor actually.
Any machines textbook it's available, no?
Okay, sir. I actually many times PC. Okay, sir.
Power electronics and AC machines, sorry. Power electronics drives and machines, something. PC cell.
Okay, thank you. Sir, actually I studied repeatedly, but actually somehow concept is in lagging. Some concept is lagging.
You ask me. Okay. You ask me wherever you have a doubt, you can ask me.
Yes.
Here.
Thank you, sir. Thank you.
Okay. Hello, sir.
Pratyush, tell me.
Sir, you have said that proximity effect is due to that, not due to mutual conductor flux linkage, no, sir. Sir, that flux linkage will cause the EMF in second conductor, no, sir.
Yes.
Sir, the current will oppose the mutual flux linkages caused by the first conductor.
That is voltage drop. That's okay. One is voltage drop. Other than that, because of the EMF, there may be a circulating current creation also.
Yes, sir.
That's the eddy current.
Yes, sir.
That eddy current may disturb the actual current flow, right?
Yes, sir. Means that eddy current should oppose the the first conductor current, no, sir. Actually, the cause is that, no, sir.
It may or may not be. How you can say cause and all the things? You have to look into the conductor and you should tell. The angle is also one of the things which is playing a role there.
Okay, sir.
Sir, no?
Yes, sir. Yes, sir. Okay, sir.
Yeah. So I'm closing the session. I think nobody's having a doubt.